The stars that twinkle above us in the vast expanse of the night sky have long sparked a sense of wonder and curiosity. Each one raises an unspoken question. What secrets do they hide? What mysteries are locked within the glowing points of light that we observe from Earth? This documentary embarks on an incredible journey, exploring the profound and complex nature of our universe. A universe where the extraordinary unfolds in ways that challenge our understanding of existence itself. As we venture deeper into the cosmos, we uncover how galaxies are born, how stars live and die, and even how distant planets far from our reach might harbor the possibility of life. Our quest to understand the universe's origins is framed by a series of compelling scientific theories, each offering a unique lens through which we glimpse the vastness of reality. Among these, the Big Bang Theory stands out as the most prominent, providing a foundation for how everything we see today came to be. Around 14 billion years ago, our universe began as a singularity, an infinitely small and dense point in space. The Big Bang marks the moment when this singularity underwent a cataclysmic expansion, releasing vast amounts of energy and setting the stage for the creation of time and space. The process was almost instantaneous. Space-time unfolded in a matter of moments, transitioning from a fiery, dense state into something more expansive and cooler, filled with fundamental particles. These basic building blocks would later combine and form the simplest elements, primarily hydrogen and helium, setting the stage for the formation of stars and galaxies. Another pivotal theory, known as cosmic inflation, posits that immediately following the Big Bang, the universe underwent a rapid and incredibly expansive growth phase. Imagine blowing up a balloon. It begins as a small dot, but with each puff of air, it expands quickly and uniformly. This inflationary period, occurring at speeds faster than light, would have evened out the universe's structure, leaving behind the uniformity we observe today. The remnants of this period are detectable in the form of the cosmic microwave background radiation, the faint glow that still lingers from the Big Bang, a telltale sign of the universe's explosive origins. In recent decades, the concept of the multiverse has gained traction among theorists, raising fascinating questions about the nature of reality itself. What if our universe is just one of countless others, each with its own set of physical laws, constants, and dimensions? Could there be other realities that exist side by side with our own, in parallel to everything we know? While the idea of a multiverse stretches the imagination, it opens up new possibilities for understanding the scope of the cosmos. Each of these theories contributes a crucial piece to the puzzle of how our universe came into being, helping scientists build a comprehensive understanding of its origins. Through the study of cosmic background radiation, the abundance of elements, and the movement of galaxies, researchers are piecing together the narrative of our universe's evolution. With ongoing advancements in technology and new discoveries constantly emerging, our knowledge continues to evolve, bringing us closer to understanding the profound mystery of how everything began. The Big Bang Theory, in particular, offers us a foundational understanding of how the universe began and how it continues to evolve. Imagine, for a moment, a balloon completely deflated, a tiny dot containing all the matter, energy, and space-time of the universe. From that singular point, the universe began to expand, gradually stretching outward. Importantly, this expansion wasn't into empty space. It was space itself stretching, with galaxies being carried along in this cosmic fabric. The farther away a galaxy is, the faster it appears to recede, a phenomenon that can be observed through the redshift of light from distant galaxies. This shift, similar to the sound of a siren fading as an ambulance moves farther away, serves as a crucial piece of evidence for the ongoing expansion of the universe. As the universe expanded, it also began to cool, providing the conditions necessary for the formation of atoms, stars, and galaxies. But the expansion didn't stop there. It's accelerating. This mysterious acceleration is driven by a force scientists call dark energy, a powerful and invisible agent pushing the universe to expand even faster. Dark energy's role in shaping the cosmos is still a profound mystery, but it is instrumental in explaining the continued expansion of the universe. As the universe continues its infinite expansion, we are left to ponder the nature of existence itself. The concept of a multiverse challenges our understanding. suggesting that our universe might not be the only one. There could be others, each with its own unique laws of physics and realities, waiting to be explored. This concept is grounded in advanced theories such as string theory and cosmic inflation. String theory, for instance, proposes that the basic units of reality are not particles, but tiny, vibrating strings. This theory hints at the possibility of multiple dimensions beyond our familiar three, opening the door to the idea that different universes may exist with distinct properties. Cosmic inflation, on the other hand, suggests that the rapid expansion just after the Big Bang could have led to the creation of bubble universes, each forming with its own unique characteristics. These bubble universes would have emerged as the universe expanded at unimaginable speeds, each isolated from one another, yet forming part of the broader cosmic fabric. While these theories remain speculative, scientists are using advanced mathematical models and indirect evidence to investigate their potential implications. By studying cosmic microwave background radiation and looking for anomalies in its patterns, scientists hope to find clues that might indicate the existence of other universes. Additionally, interpretations of quantum mechanics suggest that every possible outcome of a quantum event might create a branching universe, one where each possibility results in a separate, parallel reality. Despite the uncertainty surrounding these ideas, the multiverse theory continues to fascinate physicists, sparking debates that challenge our deepest understanding of existence. As scientists explore the fundamental laws governing not just our universe, but the very fabric of reality itself, they are pushing the boundaries of what we know, leading us to ask not just where we are in the cosmos, but how many other universes might exist beyond our reach. The story of galaxies, those vast islands of stars, gas, dust, and dark matter, begins in the earliest moments of the universe. After the Big Bang, the universe was a hot, dense place, expanding and cooling over time. In the midst of this expansion, tiny fluctuations in the density of matter began to occur, causing certain regions to become denser than others. These regions, primarily filled with hydrogen and helium gas, became the seeds for galaxy formation. As gravity acted on these dense regions, the gas began to collapse, forming stars. Think of it like compressing a handful of cotton balls. The more you squeeze, the more cotton gathers. Similarly, as gas accumulated in these areas, it became denser, eventually igniting the formation of stars. These stars, often in clusters, interacted with one another through gravity and radiation, leading to more complex processes, such as the creation of supernovae and black holes. Galaxies can take on a variety of shapes, spiral, elliptical, or irregular, depending on their composition, the dynamics of their star clusters, and their interactions with neighboring galaxies. For example, spiral galaxies, with their stunning arms of stars and gas, create a majestic view, while elliptical galaxies, appearing more rounded, contain older, redder stars. Irregular galaxies, on the other hand, have no defined shape and often show signs of past interactions or mergers. Galaxies play a pivotal role in the evolution of the universe. They are not just clusters of stars, but dynamic laboratories for cosmic processes, where new stars are born, old ones die, and the chemical makeup of the universe is continually enriched. Each galaxy offers a unique environment that influences the life cycles of stars, the formation of planetary systems, and the evolution of cosmic structures. In the end, our understanding of the universe is an ongoing journey, one that takes us from the earliest moments of the Big Bang to the farthest reaches of the multiverse. With each new discovery, we peel back another layer of the cosmos, uncovering the mysteries that lie hidden in the fabric of reality. And as we gaze upon the stars, we are reminded that the journey has only just begun. Galaxies are the magnificent and dynamic building blocks of the universe, not only providing the framework for the birth and evolution of planetary systems, but also serving as the backdrop for cosmic interactions that span unimaginable scales. These cosmic entities are far more than just collections of stars. They are the very crucibles where the potential for life is shaped through their interactions, mergers, and collisions. As galaxies collide and merge, they unleash a torrent of energy, leading to new star formation and contributing to the ever-evolving tapestry of the cosmos. The interactions of galaxies with each other also provide astronomers with a window into the history and future of the universe. Each galaxy is like a page in a cosmic history book, recording the evolution of the universe from its beginnings to its present state. Through these galactic records, we are able to trace the expansion of the universe, uncovering the conditions that have led to its current structure. Galaxies hold the keys to understanding not just where we are, but how we arrived here and where we may be headed. Two of the most intriguing and mysterious components of the universe, dark matter and dark energy, are deeply intertwined with the structure and evolution of galaxies. Though invisible to our senses, these forces play a crucial role in shaping the cosmos. Dark matter acts like an unseen scaffold, quietly but powerfully shaping the structure of galaxies and clusters of galaxies. Though we cannot observe dark matter directly, we can infer its existence by the gravitational effects it has on visible matter, such as stars and gas. Observations of galaxies spinning at speeds that would tear them apart if only visible matter existed reveal the hidden influence of dark matter. This unseen mass exerts additional gravitational pull, holding galaxies together and preventing them from flying apart. In contrast, dark energy is the force responsible for the accelerating expansion of the universe. Though gravity should, in theory, slow the expansion of the universe, observations show that the cosmos is stretching apart at an ever-increasing rate. Dark energy is thought to make up a vast majority of the universe's energy content, working against the pull of gravity and propelling the universe into an expanding future. Imagine the process of inflating a balloon. As you blow air into it, the balloon stretches, and the more you blow, the faster it expands. Similarly, dark energy acts as a mysterious engine, pushing the universe outward. Together, dark matter and dark energy form the enigmatic foundation of the cosmos. While dark matter provides the gravitational framework for galaxies to form and cluster, dark energy ensures that the universe continues to expand at an accelerating pace. Though these forces remain poorly understood, they present a profound challenge to our current understanding of physics, pushing scientists to seek answers that could revolutionize our comprehension of the universe's past, present, and future. Each new discovery takes us one step closer to unraveling these cosmic mysteries, revealing a universe far more complex and intriguing than we ever imagined. Galaxies themselves come in a dazzling array of shapes and sizes, each offering a unique glimpse into the intricate architecture of the cosmos. Spiral galaxies, perhaps the most iconic, are characterized by their flat, disc-like structures, with spiral arms that radiate outward, teeming with stars, gas, and dust. These arms are often sites of active star formation, where new stars are born in vibrant regions. At the center of these galaxies lies a dense core, typically home to older stars and, in many cases, a supermassive black hole. The combination of young stars in the spiral arms and older stars in the core creates a striking contrast in the galaxy's appearance. Elliptical galaxies, by contrast, lack the elegant spiral structure of their spiral counterparts. Instead, they present a more uniform, three-dimensional oval or elliptical shape. These galaxies are predominantly composed of older stars, which gives them a yellowish hue, as they lack the blue stars that are commonly found in younger, day star-forming regions. With minimal gas and dust available, elliptical galaxies experience little star formation, and their overall activity is much more subdued compared to spiral galaxies. However, elliptical galaxies vary widely in size, from small dwarf galaxies to massive giants containing trillions of stars. Irregular galaxies, as their name suggests, lack a defined shape and exhibit a chaotic structure. These galaxies often contain a high concentration of young stars, giving them a distinct luminosity and vibrancy. Their irregular form is often the result of gravitational interactions with neighboring galaxies, which can distort their shape and redistribute their stars, gas, and dust. Irregular galaxies can be thought of as cosmic wildcards, offering a snapshot of the universe's dynamic and unpredictable nature. Each type of galaxy offers a unique insight into the processes that shape the universe. From the formation of stars to galactic mergers and collisions, the diversity of galaxies reflects the complex, ever-changing nature of the cosmos. These galactic structures not only serve as vital clues to understanding the history of the universe, but also point to the underlying processes that continue to drive its evolution. The search for exoplanets, planets that exist outside of our solar system, has captivated astronomers for decades. To detect these distant worlds, scientists have developed several innovative techniques, with the two most prominent being the transit method and the radial velocity method. The transit method involves observing the periodic dimming of a star's light when an exoplanet passes in front of it. As the planet crosses the star's path, it blocks a fraction of the star's light, causing a temporary dip in brightness. By measuring the size of this dip and the frequency of these events, astronomers can infer the size of the exoplanet and its orbital period. The radial velocity method, on the other hand, measures the subtle wobbles of a star caused by the gravitational pull of an orbiting planet. As a planet tugs on its star, the star's motion shifts slightly, and this movement is detectable by the change in the color of the light emitted by the star. This method allows astronomers to determine the mass and orbit of the exoplanet, providing valuable insights into the dynamics of the entire system. Once exoplanets are detected, astronomers employ advanced imaging techniques and spectroscopic analysis to study their atmospheres. In some cases, they can capture direct images of exoplanets by filtering out the overwhelming light of their parent stars. By analyzing the light that passes through a planet's atmosphere during a transit, scientists can discern the specific wavelengths absorbed by various gases, allowing them to determine the composition of the atmosphere. This information is vital for understanding whether a planet could support life. The study of exoplanet atmospheres also offers clues about their potential habitability. A planet's ability to support life depends on several critical factors, including the presence of liquid water, a stable temperature, and a protective atmosphere. Liquid water is essential for life as we know it, serving as a solvent for biochemical reactions and providing a stable environment for organisms to thrive. The temperature of a planet, largely determined by its distance from its star, is equally important. A planet must reside within the habitable zone, the region around a star where temperatures are just right for water to remain in its liquid state. Neither too hot nor too cold, this zone creates the ideal conditions for life to emerge. Atmospheric conditions play a crucial role in maintaining a planet's temperature and protecting its surface from harmful radiation. A suitable atmosphere, rich in oxygen and nitrogen, for example, can support complex life forms. Carbon dioxide in moderate amounts helps regulate the planet's temperature through the greenhouse effect. Together, these factors create a delicate balance, determining whether a planet can sustain life. As scientists continue to discover and study exoplanets, they are painting a broader picture of the universe's vast diversity. From the physical characteristics of distant worlds to the potential for life beyond our solar system, the search for exoplanets deepens our understanding of the cosmos and our place within it. With each discovery, we come closer to answering the age-old question: are we alone in the universe? Geological diversity is a key aspect of planetary environments that cannot be overlooked. A planet endowed with tectonic activity has the unique ability to recycle nutrients through various processes that not only support life, but also contribute to a dynamic and varied landscape. These tectonic movements shape the planet's surface, creating mountains, valleys, and oceans, fostering a wide range of ecosystems. The geological dynamism of such planets plays a critical role in maintaining stable conditions over long geological timescales, helping the environment evolve in ways that support the continued existence of life. Equally important is a planet's magnetic field, which acts as a protective shield against the damaging effects of solar winds. These solar winds, if left unchecked, could strip away a planet's atmosphere, leaving it inhospitable. The magnetic field ensures that the atmosphere remains intact, offering a stable environment conducive to life. All of these factors, tectonic activity, geological diversity, and a protective magnetic field, create a delicate balance, making planets like Earth uniquely suited for supporting life. This understanding also informs the ongoing quest to find similar planets beyond our solar system, as we seek worlds that might harbor life as we know it. The search for extraterrestrial life profoundly influences how we explore exoplanets, planets orbiting stars beyond our solar system. Scientists are driven by the tantalizing possibility that life may exist elsewhere, compelling them to identify planets that possess the right conditions to sustain life. This pursuit sharpens the focus on specific characteristics of exoplanets, particularly those located within the habitable zone of a star. The habitable zone is a region where temperatures are neither too hot nor too cold, creating the ideal conditions for liquid water, an essential ingredient for life as we understand it. The discovery of exoplanets within this zone increases the likelihood of finding planets that could potentially support life. Instruments designed to detect exoplanets are now focusing on those within the habitable zone. Through advanced telescopes and observational techniques, scientists are able to scrutinize the atmospheres of distant planets, analyzing the light that filters through them. This light reveals the presence of gases such as oxygen and methane, which could indicate the existence of biological processes. Such discoveries guide the design of future missions, providing valuable insights into the nature of planetary systems and the potential for life beyond Earth. Advancements in technology have further expanded our ability to explore exoplanets. Space-based observatories are now collecting detailed data about distant worlds, using techniques that monitor the brightness of a star. When a planet passes in front of its star, it causes a brief dip in the star's light, a phenomenon that can be detected by telescopes. This allows scientists to estimate the planet's size, orbit, and even its atmospheric composition, regardless of whether the planet is within our solar system. Furthermore, the search for extraterrestrial life has broadened our understanding of what constitutes a habitable environment. Scientists have begun to recognize extremophiles, organisms that thrive in harsh and inhospitable conditions on Earth, as potential models for life elsewhere. These findings have led to the hypothesis that life could exist in environments previously thought to be too extreme. The goal of exploring diverse exoplanets, then, is not just to find Earth-like planets, but to expand our understanding of the wide spectrum of potential habitats for life. This ongoing exploration feeds into a cycle of discovery, where each new finding generates more questions, driving innovation and reshaping the strategies used to explore the universe. The possibility of discovering life beyond Earth not only drives scientific inquiry, but also captivates the imagination of people across the globe. This collective yearning to understand our place in the cosmos has become a shared aspiration, inspiring scientific and public interest alike. The potential to uncover signs of life on other planets is not merely a scientific endeavor. It represents a profound quest to connect with the broader universe and our role within it. The life cycle of a star begins in the vast expanse of space, where a massive cloud of gas and dust, primarily composed of hydrogen, known as a nebula, gathers under the force of gravity. As this cloud collapses inward, it heats up, and the pressure at its core increases until it becomes hot enough to ignite nuclear fusion. This marks the birth of a star. In the early stages of a star's life, hydrogen atoms fuse into helium, releasing energy in the process. This energy counters the inward pull of gravity, stabilizing the star's structure. Stars spend the majority of their lives in the main sequence phase, during which they maintain a balance between gravity pulling inward and the outward pressure generated by nuclear fusion in the core. The duration of this phase varies depending on the star's size. Smaller stars, like our Sun, can remain in this stable phase for billions of years, while larger stars burn hotter and faster, depleting their nuclear fuel more quickly. Once the hydrogen in a star's core is used up, it enters a new phase of its evolution. For larger stars, this phase involves the fusion of heavier elements as the core contracts and heats up. The outer layers of the star undergo fusion, turning hydrogen into helium, while the core continues to produce even heavier elements such as carbon and oxygen. As the core becomes increasingly unstable, the star expands and cools, entering the red giant phase. This phase is characterized by the star's outer layers being expelled in a dramatic eruption, which can dramatically alter the star's appearance. When the core can no longer support nuclear fusion, it leads to a gravitational collapse. For massive stars, this collapse results in a supernova, a violent and spectacular explosion that marks the death of the star. The energy released in this event not only ends the life of the star, but also creates elements heavier than iron, which are then scattered throughout space. These newly created elements can later be incorporated into new stars, planets, and even life, continuing the cosmic cycle. The life cycle of a massive star is a fascinating journey, one that ultimately leads to the formation of a black hole. As the star's core collapses, it becomes so dense that its gravitational pull becomes overwhelming. When the gravitational force becomes strong enough, even light cannot escape, creating a singularity known as a black hole. This boundary, called the event horizon, marks the point of no return, beyond which nothing, neither matter nor light, can escape. While black holes remain invisible, their presence can be inferred by observing their effects on nearby stars and matter. The life cycle of a massive star does not merely end in collapse. It gives rise to one of the universe's most enigmatic and powerful phenomena, a black hole. This process highlights the complex and interconnected nature of the universe, where the death of one star can lead to the birth of some of the most mysterious objects in space. Neutron stars are the remnants of massive stars that have exploded in supernova events. When a star significantly larger than our Sun exhausts its nuclear fuel, it can no longer support its own weight and collapses under gravity. The collapse causes protons and electrons to combine, forming neutrons, resulting in an incredibly dense object, often just slightly larger than the Sun, but with a size similar to that of a city. A single teaspoon of material from a neutron star would weigh as much as a mountain on Earth. Pulsars, a type of neutron star, emit beams of radiation that sweep across space as the star rotates. These beams of energy can be observed as pulses of light when they are directed toward Earth, earning them the name pulsars. Some pulsars spin at mind-boggling speeds, rotating hundreds of times per second. The radiation emitted by pulsars primarily consists of radio waves, though it can also include visible light and X-rays. These incredibly dense remnants of stars play a vital role in our understanding of the universe, providing natural laboratories to test theories of physics in extreme conditions. In addition to their importance in astrophysics, pulsars have been instrumental in the search for gravitational waves, subtle ripples in space-time caused by massive cosmic events. Through the study of pulsars and neutron stars, scientists gain new insights into the fundamental nature of the universe, pushing the boundaries of human knowledge and understanding. Pulsars, fascinating remnants of massive stars, often reside within binary systems, interacting with companion stars in ways that provide invaluable insights into the life cycles of these stellar objects. These interactions are not only instrumental in understanding stellar evolution, but they also open a window into the extreme conditions that characterize the universe. Neutron stars and pulsars, with their intensely powerful magnetic fields and rapid rotations, exemplify the incredibly hostile environments that exist in our cosmos. As such, they play a crucial role in advancing both astronomy and physics, helping scientists unlock the deep mysteries of the universe. Equally intriguing, recent discoveries surrounding black holes have led to a dramatic expansion in our understanding of these enigmatic cosmic entities. Among the most significant revelations is the confirmation of supermassive black holes existing at the centers of galaxies. Observations have revealed that these colossal objects can weigh millions, even billions, of times more than our Sun. Their gravitational influence profoundly affects the formation and evolution of the galaxies that surround them, serving as central hubs of activity and transformation. In addition to this discovery, astronomers have successfully captured the first ever direct image of a black hole located at the heart of the distant galaxy M87. This remarkable photograph, which shows the shadow of the black hole against the swirling backdrop of gas and dust, has not only provided visual confirmation of the black hole's existence, but also confirmed long-standing theories about how matter behaves under extreme gravitational forces. Adding another layer of complexity to our understanding, the detection of gravitational waves has opened a new chapter in the study of black holes. When two black holes merge, they generate ripples in the fabric of space-time itself, waves that travel across the universe. Specialized observatories on Earth have successfully detected these ripples, validating Albert Einstein's predictions about the nature of gravity. These discoveries not only confirm the fundamental aspects of Einstein's theory of general relativity, but also open up new avenues for exploring black holes and their behaviors, allowing scientists to gain fresh insights into black hole populations, their mergers, and the dynamics of these cosmic giants. Moreover, intriguing studies have suggested that black holes might not be entirely black, as their name implies. Some theories propose the existence of Hawking radiation, a theoretical form of energy emission that might escape from the event horizon of black holes. If such radiation exists, it could provide a deeper understanding of how black holes gradually evaporate over time. This interplay between black holes and the particles surrounding them sparks fascinating discussions about the delicate balance of energy within the universe. One of the most exciting areas of research today involves the potential connection between black holes and dark matter, an elusive and mysterious substance that makes up a significant portion of the universe's mass. Scientists are investigating whether black holes interact with dark matter, a discovery that could revolutionize our understanding of both phenomena. If a connection is found, it could reshape our cosmic models and help clarify the fundamental makeup of the universe. These findings are just the beginning of a much larger quest. With each new discovery about black holes, existing theories are tested and new questions arise, pushing scientists to continue their pursuit of knowledge about the cosmos's most enigmatic objects. At first glance, studying black holes might seem nearly impossible. After all, these objects do not emit light like other celestial bodies. However, astronomers have developed clever techniques to observe them indirectly. One of the most widely used methods involves examining the behavior of nearby stars and gas clouds. When a black hole is surrounded by material, it forms an accretion disk, a swirling vortex of matter that is gradually drawn into the black hole's gravitational pull. As this matter spirals inward, it heats up, emitting intense radiation, particularly in the X-ray spectrum. By analyzing the emitted light, astronomers can infer the presence, size, and other characteristics of the black hole. Another critical approach to studying black holes involves examining their gravitational influence on nearby stars and gas clouds. Much like how a heavy object placed on a stretched sheet causes the fabric to warp, a black hole's immense gravitational pull alters the orbits of nearby celestial objects. By observing how these stars and gas clouds move, scientists can calculate the mass of the black hole and assess its gravitational impact on the surrounding region. In addition, the detection of gravitational waves, tiny ripples in spacetime generated by the acceleration of massive objects, such as the collision of two black holes, has added a new dimension to the study of these mysterious objects. These waves travel across the universe, and when detected by sensitive instruments on Earth, they offer crucial insights into the dynamics of black holes, their mergers, and the forces at play in these cosmic collisions. Technological advancements, such as the Event Horizon Telescope, have further expanded our ability to study black holes. This innovative instrument captured the first ever image of the shadow cast by a black hole, located at the center of the galaxy M87. The image revealed the black hole's shadow against the glowing material of its accretion disk. This groundbreaking achievement provides direct visual evidence of black holes and further deepens our understanding of these cosmic giants. Through these diverse observational techniques, ranging from indirect observations of surrounding stars and gas clouds to the detection of gravitational waves, to capturing images of black holes themselves, scientists are steadily piecing together the intricate puzzle of black holes. As they continue to uncover the mysteries of these objects, they are simultaneously expanding our knowledge of the universe as a whole. Cosmic rays, high-energy particles that constantly bombard Earth from deep space, add another layer of complexity to our understanding of the cosmos. These particles are primarily protons, positively charged particles found in atomic nuclei, but they can also consist of heavier atomic nuclei and even electrons. Traveling at nearly the speed of light, cosmic rays carry vast amounts of energy, sometimes exceeding what we can generate in particle accelerators here on Earth. The origins of these cosmic rays are just as fascinating as their properties. While some are emitted by our sun, a significant portion comes from beyond our solar system. Many appear to originate from the explosions of massive stars known as supernovae, or from the powerful emissions of active galactic nuclei, regions surrounding supermassive black holes at the centers of distant galaxies. These high-energy particles provide valuable information about the most energetic and dynamic processes in the universe, shedding light on the behavior of stars, black holes, and the forces that govern the cosmos. However, not all sources of cosmic rays have been definitively identified, and this uncertainty adds an intriguing layer to the puzzle for scientists. These enigmatic particles continue to captivate researchers, leading them into deep investigations to uncover their origins. Cosmic rays, high-energy particles that bombard Earth from deep space, interact with the atmosphere in complex ways. As these rays collide with atoms in Earth's atmosphere, they can trigger cascading reactions, producing secondary particles detectable at ground level. This interaction offers more than just a glimpse into distant corners of the universe. It also presents challenges and opportunities for technology and biology. Cosmic radiation's effects on technology and living organisms are subjects of increasing concern. From the delicate electronics aboard satellites to the radiation exposure experienced by astronauts in space, the consequences of cosmic rays are far-reaching. The impact on Earth's climate has also become a topic of discussion. Could cosmic rays influence weather patterns or global temperature trends? These questions fuel further investigation, as scientists work to unravel the mysteries of radiation's role in shaping our environment and future. The study of cosmic rays serves as a window into some of the most profound mysteries of the universe, including the existence of dark matter and insights into the early conditions that led to the formation of our universe and verse. Each discovery, though often just a small piece of a much larger puzzle, pushes the boundaries of what we know about the cosmos. They provide us not only with answers, but also raise even greater questions about the nature of existence. And with each breakthrough, the universe's complexity becomes more apparent, revealing new layers that challenge our understanding of the fundamental laws of physics. In the quest to measure the vast distances between objects in the universe, astronomers have developed several ingenious techniques. Each method is tailored to the scale of the distance in question, allowing scientists to navigate the immense voids between celestial bodies. One of the earliest methods is parallax, a technique rooted in simple observation. It relies on measuring the apparent shift in the position of an object as seen from two different points in space. Think of it like holding a finger up to your face and closing one eye, then switching eyes. The finger appears to shift position relative to the background. Astronomers use this same principle to measure the distance to nearby stars, relying on the shift in their apparent position as Earth orbits the Sun. For stars further away, astronomers turn to the property of luminosity. Certain types of stars, such as Cepheid variables, have a predictable pattern of pulsation. By measuring their apparent brightness from Earth and comparing it with their known intrinsic brightness, scientists can estimate how far away these stars are. This method hinges on the relationship between a star's brightness and its distance from Earth, enabling astronomers to chart distances across the vast stretches of space. As we venture even farther into the cosmos, astronomers use a different phenomenon known as redshift. When an object in space moves away from us, the light it emits stretches out, shifting toward longer wavelengths, or the red end of the spectrum. By analyzing this redshift, scientists can determine how quickly an object is receding from Earth and calculate its distance based on the correlation between the speed of recession and distance. This relationship is captured in Hubble's law, a fundamental principle that has guided our understanding of cosmic distances. For galaxies billions of light years away, astronomers often rely on a combination of methods, using distance indicators and reference points like supernovae. These stellar explosions, occurring in certain types of stars, emit a consistent amount of light, making them a reliable standard candle for measuring vast distances. These supernovae allow scientists to estimate distances in regions of space that would otherwise be incomprehensible. These diverse techniques, when used together, form an extensive toolkit that astronomers rely on to map out the structure of the universe. The use of these methods, parallax, luminosity, redshift, and standard candles, help scientists piece together a more complete understanding of the vast, interconnected expanse of the cosmos. The distances involved are staggering, and each discovery adds a new dimension to our knowledge of the universe's complex architecture. Our journey to comprehend the size and scale of the universe has evolved dramatically over centuries. In the early days of human thought, many believed that Earth stood at the center of the cosmos, a geocentric view that placed the stars and planets in a small, finite sphere above us. This limited perspective, though widespread, constrained the scope of our understanding about the universe's true scale. During the Renaissance, thinkers such as Nicolaus Copernicus introduced a revolutionary idea, the heliocentric model. This concept suggested that Earth orbits the Sun, not the other way around. This shift in perspective not only expanded our understanding of the solar system, but also opened up possibilities for exploring much greater cosmic distances. The invention of the telescope in the 17th century further revolutionized our view. Astronomers like Galileo Galilei used the telescope to make groundbreaking observations, such as identifying the moons of Jupiter and documenting the phases of Venus. These discoveries provided clear evidence supporting the heliocentric model and hinted at a far larger and more complex universe than anyone had previously imagined. By the 19th century, astronomers were beginning to measure the distances to nearby stars using the technique of parallax. This method allowed scientists to confirm that the stars were not only far away, but also part of a vast, scattered cosmos, vastly more extensive than the sun-centered solar system. The 20th century brought a new wave of discoveries, most notably through the work of Edwin Hubble. Hubble's observations revealed something astonishing. Galaxies are moving away from us. This indicated that the universe itself was expanding, which contradicted the long-held belief that the universe was static. Hubble's work led to the formulation of Hubble's law, which quantifies the relationship between a galaxy's distance and its velocity. Essentially, the farther a galaxy is from us, the faster it appears to be receding. This discovery reshaped our understanding of the universe, suggesting that it had not always existed in its current state. Instead, it had evolved from a hot, dense origin, an idea that eventually gave rise to the Big Bang Theory. Hubble's work didn't just change the course of cosmology, it also had profound implications for how we view our place in the cosmos. No longer were we at the center of a static universe. Instead, we are participants in an ever-expanding cosmic story that is continually unfolding. Today, with powerful telescopes and space probes, we can map out the observable universe in ways that would have been unimaginable just a few decades ago. We now know that the universe is so vast, so incomprehensibly large, that the observable portion is only a tiny fraction of the whole. Beyond this lies the unknown, filled with dark matter and dark energy, mysterious components that appear to make up the majority of the universe's mass and energy, but remain elusive to our understanding. The universe's scale is no longer a matter of speculation. It is a fact, a grand reality that stretches across time and space, full of galaxies, stars, and cosmic phenomena. With each new discovery, we are compelled to reevaluate our place in the grand scheme of things, continually pushing the boundaries of human curiosity and the search for knowledge. Each new revelation adds layers to the unfolding story of the universe, encouraging further exploration and deepening our sense of wonder. As science progresses, the mysteries of the cosmos seem both daunting and exhilarating, each discovery revealing just how much we have yet to learn. Albert Einstein's theory of relativity stands as one of the most revolutionary ideas in the history of science. It seamlessly combined two separate realms of thought, space and time. For centuries, these concepts were viewed as distinct entities, independent of each other. But Einstein's genius lay in fusing them into a single dynamic entity, space-time. This breakthrough altered the fundamental understanding of how the universe operates, showing that space isn't a fixed, unchanging backdrop, and time is not a constant river. Instead, both space and time are interconnected and subject to the influence of mass and gravity. At the heart of this groundbreaking insight lies the concept of space-time curvature. To understand this, imagine the fabric of space and time as a stretched trampoline. Place a massive object, like a planet or a star, onto the fabric. The trampoline sags under the weight of the object, creating a distortion. Smaller objects, like marbles, will roll toward the center of this curvature. In the real universe, stars, planets, and galaxies behave in much the same way. They bend the fabric of space-time, influencing the movement of objects that pass nearby. This effect is responsible for governing the orbits of planets, as well as the trajectories of light itself. When light passes near a massive object like a galaxy or a black hole, its path bends, a phenomenon known as gravitational lensing. This concept also gives rise to one of the most mind-bending ideas in Einstein's theory, time dilation. As an object approaches the speed of light, time slows down for it relative to an observer who remains stationary. The faster an object moves, the slower its clock ticks. Imagine two twins. One stays on Earth while the other travels in space at near light speeds. When they reunite, the space-traveling twin will have aged less than the one who stayed behind. This seemingly paradoxical result is an intrinsic feature of space-time and is a direct consequence of relativity. It fundamentally alters our perception of time, showing that it is not an absolute, fixed quantity, but instead a relative, fluid experience. Relativity challenges our understanding of causality as well. Events that seem simultaneous to one observer may unfold at different times for another observer, depending on their relative positions and velocities. This reveals that time and space are not isolated, independent dimensions, but are deeply interwoven, shaping how we experience reality. As a result, questions about the nature of time, the flow of events, and the distinction between the past, present, and future become more complex and intertwined with the very structure of the universe. The dynamic, interconnected nature of space-time opens up new possibilities for understanding the cosmos. This deeper insight into the workings of the universe is made possible by the study of phenomena such as gravitational waves. These waves, first predicted by Einstein in his theory of general relativity, are ripples in the fabric of space-time itself, generated by some of the universe's most violent events. A dramatic collision between black holes or the merging of neutron stars can send these waves rippling across the cosmos. However, it wasn't until 2015 that the existence of these waves was confirmed. In that year, the Laser Interferometer Gravitational Wave Observatory, LIGO, recorded the first ever detection of gravitational waves, resulting from a black hole merger. This discovery was a historic milestone in astrophysics, providing direct evidence for the ripples Einstein had long predicted. LIGO works by using laser beams to measure incredibly tiny changes in distance caused by passing gravitational waves. When a wave passes, it slightly alters the distance between the mirrors of the detector, allowing scientists to detect these faint signals from across vast distances. The detection of gravitational waves has since become more frequent, with numerous events recorded. One particularly remarkable observation occurred in 2017 when astronomers simultaneously detected both gravitational waves and electromagnetic signals from a neutron star merger. This event marked the birth of what is now called multi-messenger astronomy, an approach where researchers study the universe using a variety of different signals: gravitational waves, light, and other cosmic phenomena. These discoveries not only confirm Einstein's theories, but also offer a new way to study the universe in ways that were once thought impossible. Time dilation and gravitational lensing are just two of the fascinating consequences of Einstein's theory of relativity. Time dilation occurs because of the warping of space-time by massive objects or intense speeds. For example, when an object falls into a powerful gravitational field, such as the one near a black hole, time slows down for that object in comparison to an observer far from the source of gravity. Imagine two clocks, one placed deep in a gravitational well and the other in a region of weak gravity. The clock in the stronger field ticks more slowly, illustrating how gravity can warp the passage of time itself. On the other hand, gravitational lensing refers to the bending of light caused by massive objects, such as galaxies or galaxy clusters. This is similar to how a curved glass lens bends light passing through it. When light from a distant star or galaxy passes near a massive object, the gravitational field of the object bends the light's path, distorting the image of the distant object. Scientists use this phenomenon to study the distribution of dark matter, a mysterious and invisible substance that doesn't emit light but still has a significant gravitational effect on visible matter. Speaking of dark matter, it remains one of the most perplexing components of the universe. Although it is believed to make up about 27% of the cosmos, it remains largely invisible to conventional observation methods. To study dark matter, researchers have designed highly sensitive detectors placed deep underground to shield them from cosmic rays and other background noise. These detectors aim to capture hypothetical particles known as WIMPs, weakly interacting massive particles, which are thought to be the key to understanding dark matter. Although no definitive detections have been made yet, scientists are optimistic that these experiments will eventually yield results. Meanwhile, astronomers continue to study the gravitational effects of dark matter on visible matter. By observing the rotation of galaxies and the bending of light around galaxy clusters, scientists can map out the distribution of dark matter throughout the universe. This indirect evidence provides crucial clues, even though dark matter itself does not emit light or energy and cannot be directly observed. On the other hand, dark energy, a mysterious force driving the accelerated expansion of the universe, is being studied through various wide-field surveys. By photographing millions of galaxies and analyzing the light from these galaxies, astronomers can measure the redshift, the shift of light towards the red end of the spectrum, caused by the galaxies moving away from us. This allows scientists to track the rate of cosmic expansion and understand how it is changing over time. Other innovative techniques, such as studying certain types of supernovae, serve as standard candles because their brightness remains constant. By comparing the brightness of these supernovae to their redshift, scientists can gather more information about the universe's expansion. As telescopes like the Euclid spacecraft and the James Webb Space Telescope gather more detailed data, scientists hope to gain deeper insights into the nature of dark matter and dark energy. These efforts may uncover new physics and provide a more complete understanding of the universe. The scientific community remains hopeful that these discoveries will not only clarify the mysterious makeup of the cosmos, but could also revolutionize our understanding of the fundamental forces shaping the universe. In this vast and mysterious universe, unseen forces play a pivotal role in shaping its evolution. Gravity, in particular, is a fundamental force that draws matter together, leading to the formation of galaxies, stars, and eventually planets. Picture the universe as a vast cosmic web where each node represents a galaxy, and the strands connecting them represent the gravitational forces binding them together. Over vast periods of time, gravity causes clusters of matter to coalesce, giving rise to the spectacular structures we observe in the night sky today. However, gravity is far from being the only force that shapes the cosmos. A far more enigmatic and invisible entity, dark energy, plays an equally crucial role, subtly influencing the universe's vast expansion. Imagine this force as an unseen hand, pushing the very fabric of space outward, stretching it ever further. This is what drives galaxies to drift apart over time, much like how dots on the surface of an inflating balloon move farther from each other as the balloon expands. This phenomenon, which took the scientific community by surprise, has forced a dramatic shift in our understanding of the universe's evolution. For years, scientists believed that gravity, the familiar force that attracts objects to one another, would eventually slow down the expansion of the universe, causing it to collapse back in on itself. However, the discovery of dark energy turned this assumption on its head. Instead of slowing, the universe's expansion is actually accelerating. The interplay between gravity and dark energy is a complex and delicate dance. While gravity pulls objects together, causing galaxies to merge and collide, it simultaneously sparks the formation of stars and the birth of new elements. These cosmic events create a dynamic and evolving universe, with each interaction leading to the formation of new structures on an ever-expanding scale. As galaxies interact, the effects of dark energy and gravity unfold in intricate ways, shaping the future of the cosmos. The ultimate question that remains is this: will the universe continue to expand forever, growing colder and emptier, or will gravity eventually overcome dark energy, causing everything to collapse in a monumental cosmic implosion? These fundamental forces, gravity and dark energy, are the invisible architects of the universe's story. They guide everything from the creation of galaxies to the ultimate fate of the cosmos itself. Understanding their influence not only illuminates the grand structure of the universe, but also deepens our appreciation for the delicate balance of forces that govern all existence. Every force and every interaction, whether seen or unseen, contributes to the ongoing narrative of the universe's journey. Recent technological breakthroughs have ushered in a new era of discovery, providing unprecedented insights into the universe's mysterious components, such as dark energy and dark matter. These elusive forces remain hidden from direct observation, yet they exert a profound influence on the structure and behavior of the cosmos. Picture dark energy and dark matter as the unseen scaffolding of the universe, shaping its form and guiding its evolution, even though they remain beyond the reach of conventional detection. One of the most significant advancements in this quest for knowledge has come the development of powerful telescopes equipped with state-of-the-art sensors. These tools allow astronomers to peer deeper into the cosmos than ever before, capturing light from galaxies and cosmic events millions or even billions of light years away. By studying the way these distant galaxies move and interact, scientists can infer the influence of dark matter. For instance, the way galaxies rotate and cluster suggests the presence of an unseen mass that provides the necessary gravitational pull to keep them intact. This indirect evidence is one of the key clues pointing toward dark matter, a mysterious substance that cannot be seen directly, but whose effects are felt throughout the universe. In addition to these groundbreaking observations, satellite missions focused on the cosmic microwave background radiation, an ancient remnant of the Big Bang, are helping scientists refine their understanding of dark energy. This radiation carries with it information from a time when the universe was much younger and much hotter. By studying slight temperature fluctuations in this radiation, astronomers can deduce how dark energy has influenced the acceleration of the universe's expansion. These fluctuations offer a glimpse into the conditions of the early universe, showing how the cosmos has evolved over time under the influence of these invisible forces. The role of computer simulations in this research cannot be overstated. Advanced models allow scientists to recreate the behavior of dark matter and dark energy under various conditions, offering a theoretical framework for understanding their effects on regular matter. By comparing the results of these simulations with actual observations, researchers can refine their models and improve their understanding of the complex interactions at play. As a result, our knowledge of the universe's hidden forces continues to grow, inching closer to a complete picture of the cosmos. Meanwhile, on Earth, experiments are underway to directly detect dark matter particles. These detectors, placed deep underground to shield them from cosmic interference, create a controlled environment where rare interactions can be observed. If successful, these experiments could provide the first direct evidence of dark matter, shedding light on one of the most profound mysteries in modern physics. Together, these innovative observational techniques, cutting-edge simulations, and experimental approaches form a powerful toolkit for understanding the universe's hidden dynamics. As we continue to probe these mysteries, our understanding of the cosmos grows ever more nuanced, bringing us closer to deciphering the true nature of dark energy and dark matter. The evidence for the universe's accelerating expansion is compelling and comes primarily from two sources: distant supernovae and the cosmic microwave background radiation. In the late 20th century, astronomers began observing a particular type of supernova, type 1A supernova, that explode in a predictable manner. By measuring the brightness of these supernovae from various distances, scientists made a surprising discovery. The farther away the supernovae, the dimmer they appeared. This suggested that these explosions were farther away than previously expected, indicating that the universe's expansion was not only ongoing, but accelerating. Since the light from these supernovae travels billions of years to reach us, they serve as a kind of time machine, offering a snapshot of the universe as it was long ago. This discovery, coupled with observations of the cosmic microwave background radiation, provided powerful evidence for the accelerating expansion of the universe. The fluctuations in this ancient radiation, which represent the remnants of the Big Bang, align with the idea of an expanding universe. Yet, when new models incorporating dark energy were introduced, they fit the data even more precisely, confirming that something unknown, something like dark energy, is responsible for the accelerating pace of expansion. As we continue to explore the farthest reaches of the universe, new discoveries await. By studying light from distant galaxies, scientists hope to uncover clues about the forces that govern the early universe. What did the cosmos look like billions of years ago when it was in a much hotter and denser state? How did it evolve into the vast expanse we observe today? These are the questions that drive modern astrophysics, and dark energy remains one of the most tantalizing keys to unlocking these mysteries. The future of cosmology lies in unraveling the nature of dark energy. This force, responsible for accelerating the expansion of the universe, holds the potential to reshape our understanding of the cosmos. Will the universe continue to expand forever, growing colder and emptier with each passing moment? Or could gravity eventually win out, leading to a dramatic collapse? Each new discovery about dark energy not only reshapes our understanding of the universe's timeline, but also offers new insights into the very fabric of space itself, revealing a cosmos that is far more dynamic and mysterious than we ever imagined. The exploration of new frontiers in space science, particularly through the discovery of exoplanets, promises to redefine our search for life beyond Earth. As technology progresses, we gain the tools necessary to peer into the atmospheres of distant worlds, enabling us to identify potential biosignatures that could dramatically alter our understanding of life's existence across the cosmos. The ability to detect and analyze the chemical composition of these exoplanet atmospheres will allow us to ask profound questions about the nature of life itself, challenging our very definition of what it means to be alive in the vastness of the universe. Meanwhile, another promising frontier lies in the detection of gravitational waves. These ripples in the fabric of space and time, created by cataclysmic events such as the collision of black holes or neutron stars, offer an entirely new way to study the universe. Gravitational waves carry information about the most violent and mysterious phenomena in the cosmos, events that are invisible to conventional telescopes. With the ability to capture these cosmic signals, scientists can probe some of the universe's most enigmatic occurrences and gain a deeper understanding of its most extreme environments. As we continue our journey into the cosmos, the expanding universe holds countless untold stories. These discoveries have the potential to shift our understanding of reality itself. Each new finding not only fuels scientific curiosity, but also fosters a deeper connection between humanity and the vast, mysterious universe we inhabit. The very nature of our existence is intertwined with the ongoing exploration of the stars, galaxies, and distant worlds, and the revelations of what lies beyond have the power to transform our view of life itself. Advancements in telescope technology have played a pivotal role in enhancing our understanding of the universe's expansion. Modern telescopes, equipped with state-of-the-art imaging systems and highly sensitive sensors, allow astronomers to observe distant galaxies with unprecedented clarity. These instruments reveal not only the distances of these galaxies, but also the speed at which they are moving, offering vital clues to the ongoing expansion of the universe. One of the most important ways telescopes contribute to this discovery is through the observation of redshift. As galaxies move away from us, the light they emit stretches, shifting toward the red end of the spectrum. This phenomenon, known as redshift, is a direct result of the Doppler effect and provides key insights into the motion of galaxies. The more distant a galaxy, the greater the redshift, and the faster it appears to be receding. This observation supports the theory that the universe has been expanding since the Big Bang and continues to do so today. The more we observe, the more we learn about the cosmos' vast, ever-expanding nature. In addition to visible light, modern telescopes are also capable of detecting a broader range of wavelengths, including infrared and ultraviolet light. This expanded spectrum allows astronomers to observe cosmic phenomena in greater detail, providing a more complete picture of the universe's past and present. For instance, by examining the light emitted by early galaxies, scientists can trace the history of the universe's expansion, shedding light on how it has evolved over billions of years. This broader view of the cosmos also enhances our understanding of the formation and life cycles of galaxies, stars, and other celestial bodies. Moreover, the development of cutting-edge technologies like adaptive optics has significantly improved our ability to obtain sharp, clear images of distant objects in space. Adaptive optics systems compensate for distortions caused by Earth's atmosphere, providing high-resolution images that reveal intricate details of celestial objects. These advancements have opened new avenues for the study of galaxies, nebulae, and other cosmic structures, allowing astronomers to observe and analyze features that were previously obscured or indistinguishable. The evolution of telescope technology has not only expanded our observational capabilities, but has also deepened our understanding of the universe itself. By collecting and analyzing precise data about the movement and distribution of galaxies, scientists are piecing together the story of the universe's origins, evolution, and eventual fate. Each advancement in telescope design brings us closer to unraveling the mysteries of space and time, ultimately helping us to understand the very nature of the cosmos and our place within it. Gravity, the invisible force that governs the cosmos, is a fundamental player in shaping the formation and movement of celestial bodies. From the tiniest particles to the most massive galaxies, gravity is the force that keeps everything in motion. At its core, gravity acts as a pull, attracting objects toward one another based on their mass. When a star or planet forms from a cloud of gas and dust in space, gravity causes the particles to clump together. As more mass accumulates, the gravitational pull strengthens, attracting even more surrounding matter. This process can lead to the birth of a new star, which, through nuclear fusion, begins to shine and light up the universe. Once celestial bodies form, gravity continues to govern their movements. For example, planets orbit stars due to the gravitational pull of those stars. This relationship is not dissimilar to swinging a ball on a string. As you move your arm, the ball travels in a circular path because of the tension pulling it inward. In a similar way, planets remain in their orbits, constantly influenced by the gravitational forces of their stars. Moons follow planets, and the entire solar system is bound together by this invisible force, which maintains a delicate balance between inertia and gravity. Gravity also plays a critical role in phenomena such as tides. The gravitational pull of the moon and the sun affects Earth's oceans, causing the rise and fall of tides. This force extends beyond Earth, influencing the movement of stars within galaxies. In regions where gravity is especially intense, such as near black holes, its effects are even more dramatic. Near these cosmic giants, gravity bends light and warps space-time, creating extraordinary phenomena like gravitational lensing, where light from distant objects is distorted by the immense gravitational field. Gravitational waves, ripples in the very fabric of space-time, are caused by some of the most energetic and catastrophic events in the universe, such as the collision of black holes or neutron stars. Imagine throwing a stone into a calm pond. The ripples spread out, distorting the surface. Similarly, when two massive objects accelerate in space, they create waves that travel across the universe at the speed of light. These disturbances provide a new way to observe cosmic events that are other visible to traditional telescopes, which rely on electromagnetic waves like light to study celestial bodies. Gravitational waves offer scientists a unique opportunity to explore phenomena that would otherwise remain hidden, providing a deeper understanding of the universe's most violent processes. As our ability to detect these waves improves, they promise to revolutionize our approach to studying the cosmos, opening up new ways to observe the universe's most mysterious and energetic events. With each discovery, we move closer to unraveling the intricate workings of space-time itself. However, many significant cosmic events, such as black hole mergers, emit little to no visible light, offering us only a glimpse of their power and complexity. Yet, in the quiet fabric of space, gravitational waves serve as a new window into the universe, providing a profound way for scientists to hear the cosmos in ways never before possible. These waves, ripples in space-time caused by massive objects in motion, carry with them an invaluable wealth of information about the most dramatic and elusive events in the universe. Through the careful analysis of these gravitational waves, researchers are able to extract vital details about the objects involved in such events. Details like their mass, spin, and how they interact with each other in deep space. This data significantly enhances our understanding of the life cycles of stars, the formation of black holes, and even the fundamental processes that govern the cosmos. It is as if gravitational waves unlock the secrets of the universe, helping us to understand the intricate dance of celestial bodies and the forces that shape their behavior. Moreover, these waves not only refine our understanding of astronomical phenomena, but also push the boundaries of fundamental physics itself, opening doors to exploring the nature of gravity and possibly revealing new forces or phenomena that have yet to be discovered. Gravitational waves, in their essence, are not just a tool of observation. They act as cosmic messengers, telling us stories about the universe, stories that light alone can never reveal. The discovery of these waves has revolutionized our comprehension of the universe, challenging long-held notions and offering fresh perspectives on the nature of reality itself. Albert Einstein's theories provided the foundation for this new understanding, especially through his general theory of relativity, which marked a paradigm shift in our perception of gravity. Before Einstein, gravity was understood simply as a force, a pulling attraction between objects, as described by Isaac Newton. However, Einstein proposed a radical new idea. Gravity is not merely a force, but a distortion in the fabric of space and time itself. Imagine space and time as a vast, flexible sheet. When a massive object, such as a planet or star, sits on this sheet, it creates a curve or dip in the surrounding space-time. Any smaller object that comes close will follow the curve, not because it is being pulled by a force, but because the very structure of space-time is guiding its path. This insight not only explains the orbits of planets, but also clarifies why light bends when passing near massive objects, a phenomenon we now refer to as gravitational lensing. This bending of light had been puzzling under the Newtonian framework, but made perfect sense under Einstein's revolutionary ideas. Einstein's theories also reshaped our understanding of time itself. Near massive objects, time appears to slow down, an effect known as time dilation. Observers close to such masses experience time differently than those farther away. This discovery altered our fundamental understanding of the universe, illustrating how space and time are interconnected dimensions, each shaped by the presence of mass. Far from merely providing a new equation, Einstein's work transformed gravity into an essential element of a unified reality, where space, time, and mass are all intrinsically linked in a dynamic relationship. The search for extraterrestrial life, meanwhile, presents its own set of challenges, each one as vast and complex as the universe itself. The enormity of space is the primary obstacle. The universe is so vast, billions of galaxies, each filled with billions of stars, that searching for life among this vast expanse is like trying to find a needle in an unimaginably large haystack. But even if we narrow the search, we face the limitations of our technology. Current instruments are designed to detect specific biosignatures, such as particular gases in a planet's atmosphere that could point to life. Yet, these measurements are delicate, and subtle variations can easily lead to misinterpretation. Adding another layer of difficulty is the sheer distance to most of these planets. Many lie light years away, making direct observation or communication nearly impossible. To overcome this, scientists must rely on indirect methods and sophisticated models to infer which planets might be capable of sustaining life. And even then, there's the issue of defining what life actually is. Most searches focus on carbon-based life forms, those similar to us, dependent on water and oxygen. But this Earth-centric approach might limit our perspective, excluding forms of life that could exist under entirely different conditions, perhaps based on elements or processes we have not yet considered. Despite these challenges, there have been remarkable breakthroughs. Advancements in telescope technology have enabled scientists to analyze the atmospheres of exoplanets, planets orbiting stars outside our solar system. By studying the light passing through these atmospheres, researchers can identify chemical signatures that suggest the presence of life-sustaining conditions, like oxygen, methane, or water vapor. These discoveries are tantalizing hints that we are moving closer to answering the age-old question of whether we are truly alone in the universe. Moreover, the discovery of extremophiles, organisms that thrive in some of Earth's most hostile environments, has radically expanded the possibilities for life elsewhere. From deep-sea hydrothermal vents to the frozen poles, life on Earth can endure in conditions once thought impossible. This opens up new frontiers for exploration, suggesting that life could exist in places we once deemed uninhabitable, such as beneath the icy crusts of moons like Europa or in the sulfurous clouds of Venus. Projects like NASA's Mars rover missions have made tangible progress in exploring the potential for life beyond Earth. Each successful mission yields more data, helping to clarify the conditions of other planets and moons within our solar system. At the same time, the global scientific community has become more collaborative, accelerating the pace of discovery. As researchers share knowledge, ideas, and findings, we move ever closer to the day when we may uncover definitive evidence of extraterrestrial life. The pursuit of extraterrestrial life is as much about scientific inquiry as it is about adventure. It is a journey into the unknown, driven by curiosity and the hope that we are not alone. Each setback is a learning experience, and every breakthrough offers a renewed sense of possibility. In this quest, we are not only searching for life elsewhere, but for our own place in the cosmos. When scientists detect signals from space that might indicate extraterrestrial life, they follow a meticulous process to confirm their origins. The first task is to establish whether the signals are natural or artificial. Researchers examine the signal's characteristics, whether they are regular, rhythmic, or random. Signals with repetitive intervals, for instance, may point to an intelligent source, potentially signaling a form of communication. Radio waves, in particular, are carefully analyzed for patterns that could mirror human-made communication. The search for life often involves identifying specific elements, such as certain gases in a planet's atmosphere, that could indicate biological activity. Once a potential signal is identified, scientists compare it with known cosmic phenomena, like pulsars or quasars, to ensure it's not simply a natural occurrence. This comparative analysis forms the foundation of hypotheses about the existence of intelligent life elsewhere in the universe. Despite the excitement that comes with such discoveries, scientists remain cautious. They emphasize the need for supporting evidence before jumping to conclusions. When a signal is deemed worthy of further investigation, interdisciplinary teams of astronomers, biologists, and data scientists work together to design targeted observational strategies. It's a rigorous process of questioning, testing, and refinement, a continuous pursuit of knowledge in the hope that we might one day make contact with another form of life in the cosmos. One of the most promising regions in the search for extraterrestrial life is the so-called Goldilocks zone, or the habitable zone. This zone refers to the distance from a star where conditions are just right for liquid water to exist, neither too hot nor too cold. Since water is essential for life as we know it, planets within this zone are prime candidates for hosting life. Certain types of stars, particularly M dwarfs or red dwarfs, are especially appealing. These stars have long lifespans, potentially offering their planets ample time for life to evolve. In this vast, ever-expanding universe, the search for life is not just a scientific endeavor. It is a fundamental question about our place in the cosmos. Many of these stars are known to host multiple planets, which significantly increases the likelihood of finding habitable environments. The possibility of life beyond Earth has always captured the human imagination, and the discovery of such planetary systems raises the chances of uncovering life in the universe. But the excitement doesn't stop at these distant exoplanets. Another intriguing area lies around the gas giants of our galaxy, especially their moons. Moons such as Europa and Enceladus, located within our own solar system, exhibit fascinating characteristics that suggest they might harbor conditions suitable for life. Beneath their thick layers of ice, scientists believe these moons could contain subsurface oceans, an environment where life as we know it might thrive. In addition to moons, exoplanets themselves may harbor potential for life. Some of these planets have been found to possess atmospheres rich in elements that we associate with biological processes, such as oxygen and methane. These chemical signatures are exciting because they suggest that the conditions necessary for life, especially life as we understand it, could exist on planets orbiting distant stars. The importance of these findings cannot be overstated. We are witnessing a growing body of evidence that suggests the universe may be more hospitable to life than we once thought. Yet, another promising location for life may be the regions where stars are born. These stellar nurseries are dense clouds of dust and gas where new stars and planets form. In these environments, complex organic molecules, some of the very building blocks of life, can come together. These areas are not just voids in space, they are potential hotspots where the very essence of life could be formed. As stars continue to be born, these regions may hold the keys to unlocking the origins of life itself. All these locations, scattered across the cosmos, weave together a tapestry of possibilities. They present opportunities for exploration, for discovery, and for the ultimate quest to answer the age-old question of whether life exists beyond our home planet. The hunt for life is not just about finding extraterrestrial organisms. It's about understanding our place in the universe and the conditions that allow life to flourish. Each discovery adds a new layer to our knowledge, creating a broader, more vibrant picture of the universe and its potential. Throughout the history of science, brilliant minds have shaped our understanding of the cosmos. Each of these visionaries has contributed unique insights and groundbreaking discoveries, building on the work of those who came before them. One of the earliest figures to challenge conventional wisdom was Galileo Galilei. Armed with a newly invented telescope, Galileo observed celestial bodies in ways that had never been done before. He uncovered mountains and craters on the moons of Jupiter, and the phases of Venus. These discoveries revolutionized our understanding of the heavens and set the stage for modern astronomy. Following in Galileo's footsteps, Sir Isaac Newton made monumental strides in explaining the forces that govern the universe. His formulation of the laws of motion and universal gravitation provided a framework that allowed us to understand how objects, from falling apples to distant planets, interact in the cosmos. Newton's work laid the foundation for classical mechanics, which has since become the cornerstone of physics. In the 20th century, the landscape of our understanding of the universe was transformed by Albert Einstein. His theory of relativity redefined concepts of time and space, suggesting that gravity was not a simple force, but a curvature in the very fabric of space-time. This groundbreaking shift fundamentally altered our view of the universe, highlighting the interconnectedness of time, space, and mass in ways that we had never before imagined. Equally significant was the work of Edwin Hubble, who expanded our understanding of the vastness of the universe. Through his observations of distant galaxies, Hubble demonstrated that the universe was not static, rather, it was expanding. His discoveries formed the basis for what we now know as the Big Bang Theory, the idea that the universe had a beginning and that it continues to stretch outward has become a cornerstone of modern cosmology. More recently, the work of scientists like Stephen Hawking has deepened our understanding of the most enigmatic phenomena in the universe, such as black holes and the nature of time itself. By merging the principles of quantum mechanics with Einstein's theory of general relativity, Hawking offered new insights into the mysteries of the universe's most bizarre objects. His work continues to influence the way we think about time, space, and the ultimate fate of the universe. These scientists, along with many others, have collectively pieced together the puzzle of the cosmos. Each discovery, each breakthrough has brought us closer to understanding the nature of our existence in an ever-expanding universe. Their work continues to inspire new generations of scientists and explorers, pushing the boundaries of knowledge ever further. At the heart of our ability to explore space and make these discoveries lies technology. The advancements in technology have enabled us to journey further into space than ever before. Central to this progress has been the evolution of rocketry. Early rockets struggled to escape the Earth's gravitational pull, but breakthroughs in materials science and propulsion technology have led to the development of powerful engines capable of carrying massive payloads into space. These advances have made space exploration not just possible, but increasingly feasible. One of the most revolutionary developments has been the introduction of reusable rockets. This innovation has dramatically reduced the cost of accessing space, opening the door to more frequent and ambitious missions. The ability to launch, land, and relaunch rockets is transforming the way we explore the cosmos, providing us with the flexibility to carry out more diverse and complex missions. Equally important are the advancements in instrumentation. Sophisticated telescopes and sensors have enabled us to peer deeper into space, revealing hidden details about distant galaxies, planets, and even exoplanets with conditions that might support life. These instruments gather an enormous amount of data, which scientists can use to simulate the conditions of these distant worlds, even though they remain far beyond our physical reach. Communication technology has also been a game changer. High-frequency communication systems now allow spacecraft to transmit data back to Earth in real time. This means that scientists can receive information instantly, analyze it, and make decisions based on the findings, sometimes within minutes. This instantaneous exchange of data is critical for the success of missions, allowing scientists to adjust strategies, correct course, and optimize mission outcomes. Together, these technological advancements have formed the backbone of our space exploration efforts, enabling humanity to venture farther into the cosmos and uncover the mysteries that lie beyond our planet. As we continue to push the boundaries of what is possible, the exploration of space will undoubtedly reveal new worlds, new phenomena, and perhaps new forms of life. The journey is just beginning, and the discoveries yet to come could be even more profound than those that have already shaped our understanding of the universe. Advancements in artificial intelligence, AI, and robotics have recently begun to play an increasingly vital role in space exploration. Autonomous rovers and spacecraft are now capable of performing intricate tasks independently, with minimal oversight from mission control. These machines can explore hostile environments that are far too dangerous for humans to enter. They can collect samples, take measurements, and, most remarkably, make real-time decisions without human intervention. This technological leap significantly broadens our ability to explore and understand distant worlds, opening up opportunities that were once unimaginable. Looking toward the future, innovations like 3D printing and cutting-edge life support systems are expected to revolutionize long-duration space missions. These technologies could enable human space travel to far-off destinations like Mars, allowing astronauts to sustain themselves for extended periods. Each new technological breakthrough not only pushes the limits of space exploration, but also brings us closer to answering the profound questions about life beyond Earth. Every advancement offers a fresh perspective on the universe and our place within it, transforming every mission into a journey toward deeper scientific discovery. This relentless pursuit of knowledge is powered by interdisciplinary collaboration, which has become a cornerstone of modern cosmic research. When scientists from various fields unite, they bring a diversity of perspectives and expertise that can turn a single idea into a transformative breakthrough. For instance, astronomers studying distant stars may collaborate with physicists to probe the fundamental forces shaping the universe. This cross-disciplinary approach allows for more comprehensive investigations into phenomena like supernovae or black holes, merging observational data with theoretical models. A notable example of this kind of collaboration is the landmark discovery of gravitational waves. To successfully observe these ripples in space-time, teams of physicists, engineers, computer scientists, and data analysts work together to develop the required equipment, interpret the complex signals, and share the findings across a range of platforms. This effort not only led to a new method of observing the universe, but also highlighted the immense value of cross-disciplinary partnerships in achieving monumental scientific progress. Moreover, such collaborations often result in the development of innovative technologies that benefit not only the field of space exploration, but also broader scientific endeavors. Techniques from fields like biology and materials science, for example, have been applied to improve the precision and sensitivity of space instruments. These advancements allow for more accurate measurements and deeper understanding of the cosmos. The exchange of knowledge between disciplines creates a synergy that accelerates discovery and fosters a collaborative spirit of innovation. The sharing of findings across different scientific fields also plays a crucial role in engaging the public. When complex research is conveyed in accessible terms, it sparks curiosity among diverse audiences and generates widespread support for space exploration. The idea that understanding the universe is a collective human endeavor transcends the boundaries of individual sciences, and as more people become captivated by the wonders of space, the demand for continued research and exploration only grows. One of the most profound contributions to our understanding of the universe is the discovery of the cosmic microwave background, CMB. This faint glow, which permeates the entire universe, is a remnant from the early stages of the cosmos and serves as a snapshot of the universe's infancy. Imagine the universe as a primordial soup of particles and energy. Approximately 300,000 years after the Big Bang, the universe cooled enough for protons and electrons to combine, forming hydrogen atoms and allowing light to travel freely. This light, emitted as the universe transitioned from opaque to transparent, has since stretched and cooled into microwave radiation. The CMB is often referred to as the afterglow of the Big Bang, offering a direct glimpse into the universe at a time when it first became transparent. Its existence is a key piece of evidence supporting the Big Bang theory, providing confirmation that the universe had a hot, dense beginning. The minute fluctuations in temperature within the CMB are of particular importance as they represent the early density variations that ultimately led to the formation of galaxies and large-scale structures in the universe. Furthermore, by studying the CMB, cosmologists can glean important details about the universe's age, composition, and rate of expansion. The subtle variations in this radiation provide clues about the forces that govern the universe, including the enigmatic dark matter and dark energy that seem to make up the majority of its mass. The CMB thus acts as a cosmic map, guiding scientists through the universe's evolution and helping them piece together its origins and future. The journey to uncovering the CMB began in the mid-20th century, when scientists were investigating the origins of radio waves. In the early 1960s, researchers Arno Penzias and Robert Wilson were working with a sensitive radio telescope in New Jersey when they encountered an unexpected phenomenon. No matter where they pointed their instrument, they consistently picked up a faint signal coming from every direction in the sky. Initially, Penzias and Wilson considered several possible explanations for this persistent noise, including interference from nearby sources or even a pigeon nesting within their telescope. But as they ruled out various hypotheses, it became clear that the signal they were detecting was something far more profound, evidence of the universe's earliest moments. This discovery ultimately led to a breakthrough in cosmology, revealing a profound clue about the universe's origins. The faint microwave radiation that Penzias and Wilson detected was in fact the elusive cosmic microwave background, confirming predictions made by earlier theoretical models and reshaping our understanding of the universe's birth. This serendipitous moment marked a pivotal point in scientific history, exemplifying how curiosity, collaboration, and innovation can converge to unravel the deepest mysteries of existence. However, their exhaustive investigations left these possibilities behind, marking a critical turning point in our understanding of the cosmos. Meanwhile, across the country, a group of researchers led by the visionary George Gamow and his collaborators were crafting an entirely new theory that would soon reshape the way we perceive the universe itself. They theorized that the Big Bang, the cataclysmic event believed to have given birth to everything we know, had left behind a faint but detectable afterglow. This afterglow, they predicted, would be visible in the form of microwave radiation, a relic from the very beginning of time. When Arno Penzias and Robert Wilson, two scientists working at Bell Labs, stumbled upon this theory, everything suddenly fell into place. They had, quite unexpectedly, discovered what would later be known as the cosmic microwave background, CMB radiation. This faint, pervasive glow permeates the universe, providing a glimpse into a time when the cosmos was still in its infancy, hot, dense, and chaotic, just a fraction of a second after the Big Bang. Over billions of years, this radiation has cooled, now existing at a temperature just above absolute zero. The significance of this discovery cannot be overstated. The cosmic microwave background radiation is not just a fleeting phenomenon. It is one of the most crucial pieces of evidence supporting the Big Bang theory. By offering a snapshot of the universe when it was in its earliest stages, the CMB backs up the idea that the universe has been expanding and cooling ever since that explosive moment. It offers a tangible connection to the very birth of everything we know, an invaluable tool for scientists to understand how the universe evolved. Through meticulous analysis of the CMB, astronomers can uncover a wealth of information about the early conditions of the universe. The radiation reveals essential details such as the universe's density, temperature, and the distribution of matter during its nascent stages. What's even more fascinating are the subtle temperature fluctuations in the background radiation. These seemingly minor variations in the heat of the universe are not just random noise. They represent the first seeds of the large-scale structures that would eventually grow into the galaxies and clusters of galaxies we see today. These tiny differences in temperature are like the cosmic blueprint for the formation of the universe as we know it. Studying the cosmic microwave background is akin to looking at an ancient photograph of the universe in its early years. This celestial snapshot provides an unprecedented view into the primordial conditions that helped shape the cosmos. It is a critical component in understanding not just the origin of galaxies, but also the fundamental forces and processes that have governed the universe's development. Through the CMB, scientists can gather clues about the types of particles that existed, their distribution, and how they interacted, offering new insights into the complex web of physics that governed the universe's early expansion. Beyond the information it reveals about the universe's infancy, the cosmic microwave background also aids in refining our understanding of core cosmological concepts. Perhaps most importantly, it plays a crucial role in determining the rate of expansion of the universe, a factor that directly influences estimates of the universe's age. The patterns observed in the CMB help cosmologists measure the expansion rate with remarkable precision, allowing them to peer backward in time and estimate when the universe first began. This, in turn, helps us understand the dynamics that have shaped the universe's growth over billions of years. In a sense, the cosmic microwave background serves as a window into the universe's very birth, capturing a moment in time that no telescope or human eye could ever have witnessed directly. It is a relic that holds the key to understanding how everything, from the smallest particles to the largest galaxies, came to be. It's a critical piece in the puzzle of the universe's history, and as scientists continue to study it, they uncover ever more about the forces that have shaped our reality. The tools we use to explore the universe have evolved dramatically in recent decades, ushering in a new age of discovery. Telescopes, especially those positioned beyond the distortion of Earth's atmosphere, have transformed our ability to peer deep into space. Without the interference of atmospheric turbulence, these telescopes can provide incredibly sharp images of distant celestial bodies. Just like trying to view a ship on the horizon with the naked eye and then bringing it into focus with a powerful magnifying lens, telescopes have brought the farthest reaches of space into sharp, awe-inspiring detail. Thanks to these advanced instruments, we can now study the universe in ways that were once unimaginable. Telescopes are not limited to just visible light. They capture light across the entire electromagnetic spectrum, from the infrared to the ultraviolet, each wavelength offering a different perspective on the universe. This ability to observe in different wavelengths opens up new dimensions of understanding. We can now observe phenomena ranging from the birth of stars in vast galactic nurseries to the explosive remnants of supernovae. Each discovery adds a new layer to our understanding of the universe's energy, chemistry, and fundamental structure. Satellites add yet another vital component to this expanding cosmic toolkit. Orbiting the Earth or traveling through the far reaches of space, these instruments gather data without the distortion caused by Earth's atmosphere. Observatories like the Hubble Space Telescope have revolutionized our understanding, providing breathtaking images that capture the vast beauty of the cosmos while deepening our comprehension of its structure and evolution. These space-based observatories not only allow us to study the faint light from distant stars, but also to analyze the atmospheres of exoplanets and track cosmic events as they unfold in real time. As our instruments become more sophisticated, so does our understanding of the universe. With each new telescope, satellite, and discovery, we are piecing together the cosmic puzzle. What began as a faint, distant afterglow has now become one of the most crucial pieces of evidence in our quest to understand the origin, evolution, and eventual fate of everything in existence. Furthermore, advancements in technology have made these devices more accessible than ever before. The synergy between smaller, more efficient satellites and cutting-edge ground-based observatories has opened new frontiers in our understanding of the universe. What was once reserved for an exclusive group of scientists is now available to anyone with the tools and curiosity to explore. This democratization of data has created an environment of collaboration, accelerating discoveries at an unprecedented rate. Scientists, along with enthusiastic amateur astronomers, can now analyze a wealth of data from across the cosmos, transforming the field into a collective effort. Telescopes and satellites have revolutionized not only our ability to observe the universe, but also our comprehension of fundamental questions about existence. With each new discovery, they peel away the layers of mystery that surround us, unveiling both the grandeur and the complexity of the cosmos. These tools do far more than simply magnify distant stars. They serve as instruments for understanding the very nature of reality itself. What once seemed like distant abstractions, concepts of time, space, and matter, are now brought into sharper focus, encouraging us to rethink the nature of the universe and our place within it. At the forefront of these discoveries, computer simulations have become essential for interpreting the vast and often bewildering behaviors of cosmic phenomena. These simulations allow scientists to recreate the very conditions of the universe, from the formation of galaxies to the intricate dynamics of black holes. In virtual environments, they are able to simulate processes that cannot be observed directly, enabling a deeper exploration of the cosmos. The backbone of these simulations lies in sophisticated mathematical models that capture the fundamental physical laws governing the universe, laws like gravity, thermodynamics, and electromagnetism. These models form the foundation for computer programs that apply these laws to cosmic scales. The result is a digital universe, a computational replica where scientists can manipulate key variables like mass, velocity, and temperature. This computational model allows researchers to examine how different forces interact over vast stretches of time, providing insights into cosmic events like the birth of stars, the collision of galaxies, and even the formation of black holes. Through simulations, researchers can predict future outcomes and test their theories against actual data gathered from telescopes and satellites. For example, if a simulation predicts how a galaxy might evolve over billions of years, scientists can compare these predictions with real-world observations, looking for specific signatures in the data to confirm or refine their models. These simulations also serve as a springboard for new discoveries, as they often uncover unexpected phenomena that prompt further investigation. By generating new hypotheses and insights, they continue to drive the quest for a deeper understanding of the universe. Ultimately, these simulations act as a bridge between theoretical predictions and empirical observations. They reveal the dynamic, often chaotic, nature of the universe, offering a laboratory where ideas can be tested, refined, and expanded. These digital environments play a crucial role in advancing our collective knowledge, pushing the boundaries of what we know about the cosmos. Another transformative tool that has reshaped our understanding of the universe is big data. The universe is a vast, intricate tapestry woven from countless variables: stars, galaxies, black holes, and diverse chemical compositions. Each of these elements is connected in ways that are often beyond our immediate comprehension. However, with the advent of modern technology, we can now collect immense amounts of data from telescopes and satellites that observe the cosmos in different wavelengths, including visible light, infrared, and radio waves. This is data on a scale that was previously unimaginable. Consider the staggering complexity of a galaxy, each one containing billions of stars, along with gas clouds, dust, and dark matter. Traditional methods of analysis are simply not capable of processing this overwhelming volume of information. Enter big data. By harnessing powerful algorithms and computational techniques, scientists can now sift through vast data sets and identify patterns and correlations that would be beyond human capacity to detect. With the help of advanced machine learning, computers can learn from the data, continuously improving their ability to predict and classify cosmic phenomena. In studies of galaxy formation, for instance, researchers rely on big data to model how these massive structures evolve over time. By analyzing light emitted from distant galaxies, scientists can infer not just their current state, but their history, how they have interacted with the surrounding cosmic material over billions of years. This process often includes studying the distribution and structure of galaxies, which provides a roadmap for understanding how these entities grow and evolve in the context of the broader universe. The power of big data extends beyond mere observation. It enhances our ability to understand complex phenomena that would otherwise remain elusive. As the volume of data continues to grow, the potential for breakthroughs increases, with each new discovery building on the last. By integrating big data with observational techniques like telescopes and satellites, scientists are uncovering the deepest secrets of the universe, revealing a cosmos more intricate and fascinating than we could have ever imagined. Ultimately, the confluence of advanced technology, computer simulations, and big data has opened up new avenues for exploring the universe. What was once hidden in the depths of space is now within our reach, and with each breakthrough, we come closer to unraveling the mysteries of existence itself. The universe, it seems, has far more to reveal, and with these powerful tools at our disposal, we are more equipped than ever to discover what lies beyond the stars. When observing celestial events such as gravitational waves or the dramatic collision neutron stars, the role of big data becomes indispensable. By integrating signals from a network of detectors positioned across the globe, scientists can combine these pieces of data to deepen our understanding of such rare and extreme phenomena. This fusion of signals amplifies the clarity of our observations, shedding new light on the intricate workings of the universe. With big data at its core, our comprehension of fundamental physics evolves, providing unprecedented insights into the cosmos and its most extreme conditions. It serves as a cosmic lens, unveiling secrets that would otherwise remain hidden, offering scientists a more precise view of the universe than ever before. This technological advancement not only helps manage the massive quantities of data we collect, but also opens up entirely new frontiers for exploration, allowing us to peel back the layers of mystery surrounding the cosmos. As we look to the future, several upcoming space missions hold the promise of fundamentally reshaping our understanding of the universe. These missions, poised to offer groundbreaking discoveries, are set to elevate our knowledge in various branches of astronomy and astrophysics. One of the most anticipated among them is the James Webb Space Telescope. Designed to observe the universe in infrared light, this advanced telescope will allow scientists to peer into the distant past, revealing the formation of stars and galaxies just after the Big Bang. By capturing light from some of the farthest celestial objects, Webb will provide unprecedented clarity on the life cycle of stars, as well as the atmospheres of exoplanets. This data could even pinpoint environments that may harbor the conditions necessary for life. Equally exciting is the European Space Agency's Euclid spacecraft, which is set to explore the mysteries of dark matter and dark energy. By mapping the geometry of the universe with remarkable precision, Euclid will gather critical data that could illuminate the role these elusive forces play in the expansion and structure of the cosmos. Understanding dark matter and dark energy could lead to monumental shifts in our grasp of the fundamental forces shaping the universe. In addition, NASA's Artemis program, which aims to return humans to the moon, is more than just a lunar exploration mission. It is designed as a stepping stone toward future Mars missions, enriching our understanding of the moon's environment. The knowledge gained from Artemis will not only provide insights into the history of the solar system, but also lay a groundwork for further exploration of the deep space beyond. The Artemis program represents a vital step in preparing humanity for the challenges of interplanetary travel and exploration. Perhaps one of the most ambitious and promising efforts is the Mars Sample Return Mission, a joint project between NASA and the European Space Agency. This mission aims to bring Martian soil samples back to Earth for analysis, potentially answering long-standing questions about the planet's past and whether it ever hosted life. These samples could also provide essential information about Mars's geological history, potentially reshaping our understanding of habitability and the conditions necessary for life beyond Earth. Together, these missions mark a pivotal moment in space exploration, offering pieces of the vast cosmic puzzle that could forever change our perception of existence. On a global scale, international collaborations are redefining the landscape of space exploration. With the challenges posed by the vastness and complexity of outer space, no single nation can tackle these endeavors alone. By pooling resources, expertise, and technology, countries can advance at a faster pace, leading to richer scientific discoveries. A prime example of such cooperation is the International Space Station, ISS, a modular laboratory in low Earth orbit, where astronauts from various nations collaborate on experiments that benefit humanity. These range from studying human health in space to testing technologies that will aid future missions to the Moon and Mars. Such collaborative efforts also foster innovation. When countries bring their diverse perspectives and technologies to the table, they can find creative solutions to challenges that may otherwise remain unsolved. A notable example is the collective effort in Mars exploration. Multiple space agencies contribute specialized instruments or landers to a unified mission, each bringing unique capabilities to the table, all with the goal of uncovering the mysteries of the Martian surface. Moreover, international partnerships help distribute the financial burden associated with large-scale space missions. By sharing costs and technological developments, agencies are able to undertake more ambitious projects, all while strengthening diplomatic ties and fostering shared knowledge. This cooperative spirit builds a global community of scientists and engineers united in their quest for discovery. The combined efforts of these international teams not only push the boundaries of what we know about space, but also lay the foundation for future generations of explorers, scientists, and astronauts. Looking to the future, space agencies around the world have set ambitious, long-term goals for deep space exploration. Their plans reflect both our desire to understand the universe and our commitment to securing humanity's future among the stars. A major objective for the coming decades is to send humans beyond the Moon, with Mars as the primary target. Establishing a human presence on Mars would not only provide invaluable insights into the planet's past, but also aid in the search for signs of life. The data collected could be key in supporting future efforts to colonize the planet and ensure humanity's survival beyond Earth. Simultaneously, the exploration of asteroids is gaining traction. Space agencies are beginning to consider missions that could study asteroids for their potential resources, materials that could be used for space construction, fueling future spacecraft, and even contributing to the development of space-based industries. These small celestial bodies are relics from the early days of our solar system, holding vital clues about its formation and evolution. Understanding the history embedded within asteroids could also unlock secrets about the origins of life and the conditions necessary for the development of habitable worlds. These missions and their potential discoveries represent the forefront of space exploration, demonstrating humanity's relentless curiosity and determination to understand the universe. As space agencies continue to collaborate and push the boundaries of what we know, the path forward promises not only new scientific breakthroughs, but also a deeper connection between humanity and the cosmos. Advancements in technology are paving the way for groundbreaking missions to explore the outer planets, with particular interest focusing on distant destinations like Jupiter's moons. One moon, in particular, Europa, has attracted considerable attention due to its potential to harbor life. Beneath its icy surface lies an ocean that could provide conditions suitable for sustaining life. Space agencies are preparing to launch robotic missions that will conduct comprehensive studies of these mysterious worlds, exploring their environments in unprecedented detail. These missions are not only about scientific discovery, but also about collaboration on a global scale. The exploration of deep space is a monumental task, one that cannot be tackled by any one nation alone. As such, space agencies around the world are working together, pooling their resources and expertise to achieve greater scientific progress. By uniting their efforts, humanity strengthens its ability to venture further into the cosmos, opening new frontiers of knowledge. The benefits of these international partnerships are immense. Not only do they foster global scientific cooperation, but they also enhance our collective capacity to explore and better understand the universe, positioning us for the next great leap into space. The long-term goals of these missions extend far beyond the realm of science alone. As we reach for the stars, the ultimate vision of space exploration is one of survival, a plan to ensure the continuation of humanity in the event of a global catastrophe. One such aspiration is the creation of self-sustaining colonies beyond Earth, capable of supporting human life in environments light years away. While these objectives may seem distant, they are within our grasp, and their pursuit promises to revolutionize our understanding of life, the universe, and the future of humanity. This journey, however, is not without its mysteries, some of which challenge our very understanding of the cosmos. One of the greatest of these enigmas is dark matter. Though invisible to the naked eye and undetectable by traditional instruments, its existence is inferred through its gravitational effects on galaxies. Dark matter is believed to make up a significant portion of the universe's mass, yet its true nature remains a mystery. To imagine such a form of matter, omnipresent yet entirely undetectable, is to confront one of the universe's greatest challenges. Similarly, dark energy presents another profound mystery. This force seems to be responsible for the accelerated expansion of the universe, pushing galaxies apart rather than pulling them together, as gravity does. The implications of dark energy are vast, forcing us to reconsider our understanding of the universe's fate and structure. It raises questions about how the universe is evolving and what forces are at play in shaping its destiny. Then there are the fast radio bursts, brief, intense flashes of radio waves from distant galaxies. These bursts are one of the most intriguing phenomena in modern astrophysics, and their origins are still not fully understood. Some theories suggest they may be linked to neutron stars or black holes, yet no definitive explanation has emerged. These fleeting signals challenge our current understanding of the universe, leaving plenty of room for speculation and debate. Gamma-ray bursts, another cosmic mystery, are the universe's most powerful explosions. These extraordinary events, which occur when massive stars collapse or when neutron stars collide, release energy that can briefly outshine entire galaxies. While we have some understanding of their origins, the details behind these explosive phenomena remain elusive. Their immense power and mystery continue to captivate researchers, offering both inspiration and puzzling questions. Finally, the concept of cosmic strings adds yet another layer of complexity to our understanding of the universe. Hypothetical one-dimensional defects in the fabric of space-time, these strings may have formed in the early universe and could stretch across vast distances. If they exist, they could warp the space around them, affecting the motion of galaxies. However, despite ongoing research, no conclusive evidence for cosmic strings has been found, and their role in cosmic history remains a subject of speculation. These unexplained phenomena serve as reminders of the complexity of the universe and the vast frontiers of knowledge that remain to be explored. Each mystery offers a tantalizing invitation to dive deeper, promising new discoveries and insights into the workings of the cosmos. But how do scientists go about unlocking the secrets of the universe? The answer lies in a combination of curiosity, meticulous methodology, and collaborative effort. When confronted with cosmic events that defy explanation, researchers approach them like detectives piecing together a puzzle. The first step is to gather as much data as possible, often from a network of observatories and telescopes located around the world. These instruments are equipped with advanced technologies designed to capture a wide range of wavelengths, from visible light to radio waves and even gravitational waves. Once the data is collected, scientists begin analyzing the observations, searching for patterns or anomalies that could reveal the true nature of the event. This process is similar to solving a mystery, with researchers acting like detectives at a crime scene. They use simulations and modeling to recreate the conditions surrounding the event in an attempt to understand what happened and why. Collaboration is key in this process, as scientists from various fields, astrophysics, cosmology, and even biotechnology, bring unique perspectives to the table. By sharing their findings through conferences and publications, they foster a broader understanding of the issue at hand. Peer review plays a crucial role in this process. After the initial findings are presented, other experts evaluate the methods and interpretations to ensure that the conclusions are scientifically sound. This scrutiny helps to prevent speculation and ensures that only reliable conclusions are drawn from the data. As more information is gathered and theories are tested, some hypotheses may gain support, while others are rejected. This ongoing process of refinement allows the scientific community to gradually unveil the mysteries surrounding unexplained cosmic events. Fast radio bursts, for example, provide a fascinating window into the universe's extreme environments. These brief, intense flashes of radio waves, which last only a fraction of a second, come from deep space, possibly from distant galaxies. While their origins remain a mystery, the investigation into these bursts offers clues about the conditions in their host galaxies. By studying these bursts, scientists can learn more about high-energy astrophysical events such as the mergers of neutron stars or the collapse of massive stars. In many ways, these cosmic anomalies offer a glimpse into the unknown, revealing the immense complexity of the universe. As scientists continue to investigate these mysterious events, they uncover new layers of knowledge that bring us one step closer to understanding the cosmos. Fast radio bursts, FRBs, are fleeting, high-energy events that challenge our understanding of the cosmos. When these mysterious radio signals travel across the vast stretches of space, they pass through a medium, the intergalactic environment, that holds secrets about the universe's most fundamental elements. The dispersion of these signals gives scientists a unique opportunity to probe the density and composition of the matter scattered throughout the cosmos. By analyzing the way the signals disperse, researchers can infer the amount of matter embedded in these immense cosmic distances, unlocking new revelations about the unseen structures that permeate space. The enigmatic nature of FRBs doesn't just challenge current models of physics and cosmology. Each new discovery adds layers to our understanding of the universe's origins and its ongoing evolution. As we gather more data on these bursts, we refine our theories about the early universe, galaxy formation, and even the very fabric of space and time. These bursts hold the potential to offer clues about some of the universe's most energetic and mysterious processes, expanding the frontiers of our knowledge. Similarly, the evolution of galaxies is a process that unfolds over unimaginable timescales, marked by constant change and transformation. Galaxies are born from enormous clouds of gas and dust, which collapse under their own gravity, gradually accumulating mass. This process resembles the way a snowball gathers snow as it rolls downhill, with more and more material being drawn into the galaxy's core. But galaxies do not remain static. Over billions of years, they undergo continuous transformation, frequently interacting and colliding with neighboring galaxies. These cosmic encounters are not unlike two dancers meeting on a stage, their movements blending and shifting as they converge. Through such collisions, galaxies merge, giving rise to new shapes, like the transformation from spiral forms to elliptical ones. This cosmic choreography can spark bursts of star formation as gas clouds collide and compress, igniting new stars in a vibrant cosmic display. But just as galaxies evolve through dramatic events, they also go through quieter periods. Over time, as stars form and burn brightly, galaxies slowly deplete their gas reserves and star formation rates begin to decline. This marks a transition from a once vibrant hub of creation to a more peaceful galaxy, where star formation significantly slows. As this happens, the galaxy ages and the stars within it begin their gradual descent into their final stages, like dancers slowly winding down their performance. The environment surrounding a galaxy plays a crucial role in its evolutionary journey. Neighboring galaxies, cosmic gas flows, and dark matter all influence a galaxy's path. Some galaxies end up in larger groups known as galaxy clusters, where the gravitational forces between them can strip away material, altering the galaxy's developmental trajectory. Yet, throughout this entire cosmic narrative, galaxies also contribute to the greater universe in significant ways. When massive stars end their life cycles in fiery supernova explosions, they scatter heavy elements into space, enriching the surrounding environment. These elements play a key role in the formation of future generations of stars, potentially even fostering the creation of planets and life. In the grand scheme, the life of a galaxy is a dynamic, evolving story, unfolding over billions of years, shaped by gravitational forces, material interactions, and the ever-changing dance of the cosmos. Each galaxy's story is unique, an intricate tale of cosmic processes that govern the very nature of the universe. At an even larger scale, galactic clusters provide one of the most essential avenues for understanding the cosmos. These vast collections of galaxies are bound together by the invisible force of gravity, and they act like bustling cities, each neighborhood representing a galaxy with its own collection of stars, planets, and cosmic phenomena. These clusters can contain a handful of galaxies or stretch to thousands, all moving through space as a single, unified entity. Studying galactic clusters is vital for a number of reasons. First and foremost, they serve as cosmic laboratories, providing astronomers with an unparalleled opportunity to study the distribution of matter across the universe, both visible and invisible. Dark matter, which makes up much of the universe's mass but cannot be observed directly, exerts its influence through its gravitational effects. By observing how galaxies within clusters interact, scientists can deduce the presence and properties of dark matter, which is otherwise undetectable. Moreover, galactic clusters are crucial for understanding the large-scale structure of the universe. They represent the intersections between vast voids of space, marking where galaxies group together over cosmic timescales. Through the study of these clusters, researchers gain insights into the formation and evolution of galaxies, providing a deeper understanding of the universe's history. These clusters are more than just collections of galaxies. They are essential pieces of the cosmic puzzle that help us piece together the processes that have shaped the universe from its earliest moments to its current state. Through the study of FRBs, galaxy evolution, and galactic clusters, we continue to unravel the complex and intricate web of the universe. Each discovery, each new observation, not only adds to our knowledge but also inspires new questions, pushing us further toward understanding the vast and mysterious cosmos in which we exist. The more we learn, the more we realize how much there still is to explore. Clusters of galaxies are among the most awe-inspiring and complex structures in the universe. These massive groups, often containing thousands of individual galaxies, are not merely collections of stars and gas. They are dynamic environments where extreme physical conditions thrive. The temperatures of hot gas within these clusters soar to unimaginable levels, creating an environment where powerful forces are at play. These forces, through a combination of intense gravity, pressure, and energy, can lead to the formation of new stars. The study of such galactic clusters helps astronomers unlock critical insights into the life cycles of galaxies and the fascinating processes that drive their evolution. It is here, within the intricate dance of creation and destruction, that we can witness the cosmic forces shaping the universe. Through careful investigation, we gain a deeper understanding of our universe's origin, its continual evolution, and the mysterious forces that govern its every change. Galaxies are far from static. They are constantly evolving, and one of the most dramatic events in their life cycle occurs during galactic collisions. When two galaxies approach one another, their immense gravitational fields begin to interact in profound ways, distorting not only their shapes, but also the distribution of their stars, gas, and dust. At first, one might think that these massive structures would simply pass by each other in the vast emptiness of space. However, the gravitational forces between them are anything but passive. As the galaxies draw nearer, they begin to pull on one another, initiating dramatic changes. These interactions cause the galaxies to stretch and distort, forming long tidal tails, streams of stars and gas that are pulled outwards due to the immense gravitational forces. It is within these tidal streams that complex processes unfold. As clouds of gas collide and compress, it triggers bursts of star formation. These bursts introduce new, brilliant stars into the once quiet galaxies, transforming their dynamics and adding to their luminosity. If the galactic encounter is forceful enough, the two galaxies may eventually merge, creating an entirely new, larger galaxy. This merger is often chaotic, with elements from both galaxies blending together, resulting in a structure that is a mixture of the two original forms. The outcome of such collisions can vary. Some mergers produce spiral galaxies, while others form elliptical or irregular galaxies, depending on factors such as the properties of the colliding galaxies and the angle at which they collide. But these collisions do not only shape visible structures, they also have a significant impact on the distribution of dark matter. Dark matter, which makes up a substantial portion of a galaxy's total mass but cannot be directly seen, plays a crucial role in the dynamics of galaxies. As galaxies collide, the dark matter halos that surround them can shift and rearrange. This, in turn, can alter the gravitational stability of the galaxy and influence future interactions with other galaxies. In this way, galactic collisions do more than just reshape the visible structure of galaxies. They also impact the very forces that govern their gravitational interactions. These events are transformative, capable of spurring new star formation, creating new types of galaxies, and forever altering the galactic landscape. They serve as a striking reminder of the dynamic and interconnected nature of the universe, where the presence of one galaxy can completely change the fate of another. In addition to galactic collisions, one of the most powerful tools that astronomers use to explore the universe is light. Through the study of light, we do not simply observe the glowing stars or distant galaxies. Instead, we are receiving vital information about their past, present, and even their future. Light is like a messenger from the depths of space, carrying knowledge that has traveled across vast distances, sometimes millions or even billions of years, to reach us. This long journey allows light to serve as a time capsule, offering a glimpse into the distant past. One of the first tools in an astronomer's arsenal is the spectrum. When light from a celestial object passes through a prism, it disperses into a rainbow of colors, each corresponding to a different wavelength. These colors reveal essential information about the object's chemical makeup. Each element, whether it's hydrogen, helium, or any other chemical, emits or absorbs light at specific wavelengths, creating a unique signature or fingerprint for that element. By analyzing these spectral lines, astronomers can determine which elements are present in a star or galaxy, providing crucial insights into their composition and the nuclear processes that power them. Moreover, the way light behaves as it travels through space, specifically its redshift and blueshift, offers critical information about the movement of celestial objects. When an object, such as a galaxy or star, moves away from us, its emitted light stretches, causing it to shift toward the red end of the spectrum. This phenomenon is known as redshift. On the other hand, if the object moves closer to us, its light waves are compressed, creating a blue shift. This shift toward the blue end of the spectrum serves as a marker of motion, much like how the sound of a siren changes pitch as an ambulance moves toward or away from you. By studying the redshift and blueshift of light from distant galaxies, astronomers can determine the speed and direction of these galaxies. This insight is essential for understanding the expansion of the universe itself. In fact, the discovery that most galaxies exhibit a red shift led to the groundbreaking realization that the universe is expanding, a revelation that radically changed our understanding of cosmology. The study of light, then, is not just about illuminating the universe, but also about unlocking the fundamental forces and processes that govern it. Light is also a window into the history of the universe. Events such as the explosion of a supernova or the formation of a black hole emit light that travels across space, carrying with it a snapshot of those events. By examining this light, scientists can piece together a timeline that spans billions of years, helping us understand the life cycles of stars and the ever-changing nature of galaxies. In this way, light is not merely a source of illumination. It is a powerful tool that allows astronomers to probe the very fabric of the universe. Through a careful study of light, scientists have been able to unravel the mysteries of cosmic motion, the evolution of galaxies, and the ongoing expansion of the universe itself. The study of light provides the foundation upon which our understanding of the cosmos is built, offering an ongoing narrative of the universe's past, present, and future. Furthermore, the phenomena of redshift and blueshift are indispensable tools in astronomy, serving as fundamental concepts for various applications that enhance our understanding of the universe. These shifts in the light spectrum, indicating how objects move away from or towards us, play a pivotal role in exploring cosmic evolution, the dynamics of stars in different gravitational fields, and the life cycles of galaxies. In essence, red and blue shifts act as cosmic signposts, guiding us through the vast, intricate, and ever-changing fabric of the universe. They enable scientists to map the motions of celestial bodies, helping to decipher the broader narrative of the cosmos. Among the most ancient and powerful objects in the universe are quasars. These stellar entities function like cosmic time capsules, offering a glimpse into the distant past of the universe. To truly grasp their significance, imagine observing a star in the night sky. When you look at its light, you're not seeing it as it is in the present, but as it was when that light first began its journey. Now, with quasars, this concept takes on a whole new level of meaning. A quasar is the extraordinarily bright center of a galaxy powered by a supermassive black hole. As this black hole consumes material at an astonishing rate, the spiraling matter emits immense amounts of energy, making quasars visible across vast stretches of space. What makes quasars particularly intriguing is that many of the quasars we observe today originated billions of years ago, when the universe itself was still in its infancy. This means that when we look at the light from these distant objects, we are, in a sense, peering into the past, back to an era when the universe was much younger. The light from a quasar we observe today may have begun its journey only a few 100 million years after the Big Bang, providing astronomers with invaluable insights into the conditions of the early universe. By studying the light emitted by quasars, scientists can glean critical information about the formation of galaxies, the distribution of matter, and the evolution of cosmic structures over time. Moreover, quasars often emit unique spectral fingerprints that offer detailed information about the composition of the universe during the epochs in which they originated. Analyzing these spectral features enables researchers to unravel the mysteries of elements that existed in those distant times. This helps us understand how the universe evolved from its hot and dense beginnings to the vast, complex structure we observe today. In this way, quasars serve not only as distant beacons of light, but also as windows into a fascinating journey through the history of the cosmos. Mathematics, the universal language of science, is a powerful tool for understanding the intricacies of the cosmos. It acts as a toolkit for scientists, allowing them to describe, model, and predict phenomena beyond our planet. Through mathematics, complex ideas are transformed into clear, logical representations, enabling astronomers and physicists to delve deeper into the workings of the universe. For example, consider the movements of celestial bodies. These bodies do not simply exist in space. They are constantly in motion, guided by the forces of gravity. Mathematical equations are crucial in describing these movements. By understanding the relationships between different celestial objects, scientists can predict the orbits of planets around stars or the interactions between galaxies. This predictive power enables them to foresee events like eclipses or the visibility of comets from Earth. Mathematics also plays a key role in unraveling the mysteries of the fundamental forces that govern the universe. Take, for instance, the concept of gravity. Isaac Newton's laws of motion, expressed mathematically, allow us to calculate how objects will move under the influence of gravity. This foundational work paved the way for further scientific advancements, such as Albert Einstein's theories of relativity, which presented a more nuanced understanding of gravitational interactions. Einstein's equations describe how massive objects warp the fabric of space and time, enriching our ability to predict cosmic events and providing deeper insights into the nature of gravity itself. In addition, mathematics is essential for analyzing the massive amounts of data collected from telescopes, space probes, and other instruments. Scientists gather vast quantities of information, and without the aid of mathematical tools, this data could easily become overwhelming. Through the application of statistical methods and algorithms, researchers can sift through the noise, extracting meaningful patterns that may lead to groundbreaking discoveries. This includes unveiling secrets about dark matter, discovering exoplanets, and understanding the ongoing expansion of the universe. By using mathematics, scientists continue to unlock the mysteries of the cosmos, pushing the boundaries of our knowledge and expanding our understanding of the universe's origins, structure, and future. Simulations, fueled by intricate mathematical models, enable scientists to probe theoretical scenarios that are, as of yet, beyond our observational reach. These simulations serve as windows into the unknown, providing a means to explore the universe's secrets before they can be directly observed or tested. For instance, models of the early universe have offered us an invaluable understanding of how the cosmos transitioned from a dense, hot state to its present form. These models have shed light on the intricate processes that led to the formation of galaxies and the distribution of cosmic structures we see today. Without the power of mathematics, such insights would remain out of our grasp, leaving us to wonder how the universe came to be. Mathematics sits at the very core of unraveling the universe's mysteries. It is the lens through which we examine the cosmos, allowing us to make predictions, test hypotheses, and ultimately unlock the complexities that shape our existence. Without it, our understanding of the universe would be rudimentary, akin to wandering in the dark without a map. Mathematical models offer a unique capability to transform complex observations into comprehensible concepts, shaping our understanding of the universe in profound ways. One of the earliest and most transformative frameworks in this journey of discovery is Sir Isaac Newton's theory of gravity. This groundbreaking model simplified our understanding of planetary motion and set the foundation for explaining how celestial bodies interact via gravitational forces. Newton proposed that objects attract each other in proportion to their mass and the distance between them. This elegant explanation provided a clear mechanism for understanding the orbits of planets, the motion of moons, and the very mechanics of our solar system. As our understanding of the universe progressed, Albert Einstein's theory of general relativity dramatically altered our view of gravity. In contrast to Newton's view of gravity as a force, Einstein proposed that gravity is not a force at all, but rather the curvature of space and time around massive objects. To visualize this, imagine placing a heavy ball onto a stretched rubber sheet. The sheet bends and dips under the weight, mirroring how massive bodies like planets warp the fabric of space-time. This concept not only reshaped our understanding of gravity, but also explained phenomena that were previously unfathomable, such as the bending of light around massive stars and the gravitational effects within galaxy clusters. In addition to classical mechanics and relativity, quantum mechanics introduced a revolutionary new perspective on the universe, one that focuses on the behavior of particles at the smallest scales. This field uses complex mathematical frameworks to describe how particles interact with one another, allowing predictions that are experimentally verified. Concepts such as wave-particle duality and quantum entanglement have expanded our comprehension of the universe, unveiling the extraordinary and paradoxical behavior of matter and energy on a microscopic level. This field reveals an elegant and mysterious dance of particles, where matter and energy seamlessly intertwine. Mathematics also plays a critical role in cosmological models, such as the Big Bang theory, which uses sophisticated equations to describe the universe's rapid expansion from an intensely hot and dense state. These models not only detail how the universe began, but also offer insights into its current expansion and even its potential fate. By applying mathematical principles, scientists have even ventured into the realm of dark matter and dark energy, concepts that constitute a substantial portion of the universe's mass and energy, but remain elusive to direct observation. These mathematical models do more than just catalog celestial phenomena. They allow us to piece together a coherent narrative of the universe's evolution, providing a deeper understanding of its structure and the forces that govern it. Each mathematical model builds on previous observations, forming a network of interconnected ideas that continue to guide our exploration of the cosmos. These models help us interpret the vast, intricate design of the universe, creating a coherent framework that shapes our expanding knowledge. It's not merely about cataloging facts. It's about connecting the dots in ways that allow us to explore and understand the cosmic tapestry in all its complexity. Mathematical theories have formed the backbone of our space exploration endeavors. They guide everything from our comprehension of the motions of celestial bodies to the engineering of spacecraft. At its core, mathematics provides a universal language, one that unites scientists and engineers in their quest to make accurate predictions about the behavior of objects in space. The laws of motion developed by Newton remain foundational in understanding how objects move under the influence of gravity, from the orbits of satellites to the trajectories of interplanetary missions. These laws inform the design of spacecraft and guide our navigation through the vast expanse of our solar system. As humanity ventures beyond Earth, we encounter new challenges that demand increasingly sophisticated mathematical approaches. For example, predicting the path of a spacecraft involves intricate calculations that account for the gravitational pull of multiple celestial bodies, as well as the spacecraft's velocity and the subtle influences of space itself. Mathematical models are essential in simulating these factors, ensuring the success of missions that explore the furthest reaches of our solar system and beyond. These models serve as the blueprint for space exploration, transforming abstract concepts into real-world missions that push the boundaries of human knowledge and capability. In sum, the power of mathematical models extends far beyond mere numbers and equations. They are the tools through which we explore the deepest questions about the universe, tools that guide us through uncharted territories and expand our understanding of the cosmos. Through these models, we not only explain the universe's past and present, but also gain insights into its future, offering a map for navigating the cosmic unknown. The advent of Einstein's theory of relativity marked a groundbreaking shift in our perception of time and space. Prior to this, the understanding of these concepts was largely abstract, with little connection to the physical world. Yet, relativity did more than just introduce a new lens through which to view the universe. It redefined the very fabric of reality. Time and space, once thought to be immutable, became dynamic entities, bending and warping in response to gravity and motion. This transformation in our understanding has had profound implications on how we approach everything from the structure of the cosmos to the behavior of the most elusive phenomena like black holes. One of the most intriguing aspects of relativity is its ability to reshape the way we think about distances and spatial relationships. As we study cosmic events such as the expansion of the universe or the formation of black holes, we rely heavily on mathematics. This discipline allows us to give shape to ideas that, without the tools of quantitative analysis, would remain abstract and enigmatic. Mathematics serves as the bridge between the unknown and the known, providing the framework through which we explore and describe the cosmos. In the realm of astrophysics, mathematics becomes a crucial instrument for unraveling the mysteries of the universe. By creating mathematical models, scientists can simulate the behavior of stars, galaxies, and other cosmic entities. These models are not just theoretical, they have practical applications. They enable researchers to analyze data gathered from telescopes, sensors, and space probes, leading to groundbreaking discoveries about the formation of galaxies, the nature of dark matter, and even the fundamental forces that govern everything from the smallest particles to the largest cosmic structures. Without mathematics, much of what we know about space would remain elusive. It is through mathematical theory that we ask questions, design experiments, and ultimately push the boundaries of human understanding. The more we explore, the more we discover, but each revelation often opens new questions. The pursuit of knowledge is a constant cycle, propelling humanity forward into the unknown. Yet, despite the incredible progress we have made in understanding the universe, much remains cloaked in mystery. Advances in technology and theory have enabled us to probe deeper into the cosmos than ever before, but certain fundamental questions continue to elude us. One of the most significant gaps in our knowledge concerns dark matter and dark energy. Together, these two components account for roughly 95% of the universe's total mass and energy, yet their true nature remains an enigma. Dark matter, though invisible, is believed to exert gravitational influence on galaxies and clusters of galaxies. Dark energy, on the other hand, is thought to be responsible for the accelerating expansion of the universe. But despite their undeniable effects, we have yet to detect either of these forces directly or fully understand how they interact with the ordinary matter we can observe. Another area of profound uncertainty lies in our understanding of the universe's earliest moments. According to the Big Bang Theory, the universe began as a singularity, a point of infinite density where the laws of physics, as we understand them, break down. What happened during this period remains speculative, as does the rapid expansion of the universe known as cosmic inflation. How did the universe, from such a dense and infinitesimal point, explode into the vast and diverse cosmos we see today? These questions remain at the forefront of cosmological research, pushing scientists to explore the origins of everything we observe. Additionally, the enigma of black holes presents its own set of challenges. Although we have robust theories explaining what happens outside a black hole's event horizon, we remain in the dark about what occurs inside. Concepts such as the information paradox, which questions how information is preserved when matter falls into a black hole, continue to provoke debate among physicists. The inability to fully explain the nature of black holes underscores a broader issue: the ongoing tension between two of physics' most successful theories, quantum mechanics and general relativity. These theories have revolutionized our understanding of the very small, particles, and the very large, the cosmos, but they are fundamentally incompatible in their current forms. The search for a unified theory that can reconcile the laws governing the micro and macroscopic realms remains one of the greatest challenges in physics. Moreover, the quest to understand life beyond Earth has revealed yet another frontier in our knowledge. While we have discovered potentially habitable planets and the chemical building blocks of life in various corners of the universe, our exploration is still in its infancy. The search for extraterrestrial intelligence is ongoing, and the possibility of life beyond our planet challenges both our scientific ingenuity and philosophical perspectives. How do we define life, and what forms might it take on planets so vastly different from Earth? Despite these immense challenges, the search for answers continues to drive scientific discovery. Each new question that emerges only deepens our curiosity and determination to understand the universe. The progress we have made in unraveling the cosmos is remarkable, but it is clear that we are only at the beginning of a much larger journey. Each answer we uncover opens up new avenues of inquiry, and the cycle of discovery never ends. In the vast domain of cosmic exploration, uncertainty is a constant companion, but it is this very uncertainty that drives innovation. Scientists, equipped with a blend of analytical thinking, technological advancements, and creative problem solving, navigate this unknown with precision and vision. The scientific method, where hypotheses are formed, tested, and refined through observation and experimentation, forms the backbone of this exploration. Even when data is scarce or ambiguous, this structured approach allows researchers to probe deeper into the mysteries of the universe. Another critical tool in this journey is the use of simulations and models. These virtual representations of celestial phenomena, such as the interactions between distant stars or the conditions on far-off planets, allow scientists to predict behaviors and outcomes. These models are grounded in the well-established principles of physics, enabling researchers to test hypotheses and refine their theories in a controlled environment before applying them to the real universe. Collaboration is equally essential. Cosmic exploration is a multidisciplinary endeavor, requiring the combined expertise of physicists, astronomers, planetary scientists, engineers, and many others. Through collaboration, scientists share resources, knowledge, and techniques, enriching the exploration process. Working together enables them to approach problems from diverse angles and create solutions to the complex challenges posed by the cosmos. The tools of exploration, spacecraft, telescopes, and satellites are indispensable in this quest. Equipped with advanced instruments, these machines gather data across various wavelengths, from visible light to radio waves and beyond. The human eye, limited to a narrow range of the electromagnetic spectrum, cannot see the full picture. But through the use of these technologies, scientists are able to peer into the distant reaches of the universe, capturing information that reveals the hidden structures and processes at work in the cosmos. Despite all the progress made, the universe still holds many of its secrets close. But with each discovery, each breakthrough, we inch ever closer to understanding the grand tapestry that surrounds us. The journey is far from over, and the search for knowledge continues to inspire and drive humanity forward into the depths of space and time. Interpreting astronomical data is a complex endeavor, often fraught with ambiguity. This inherent uncertainty can make it difficult to draw definitive conclusions from observations of the cosmos. To address these challenges, scientists rely heavily on statistical methods, which allow them to sift through vast quantities of data and identify patterns that might otherwise remain hidden. Additionally, peer reviews serve as a crucial safeguard in the scientific process. When new findings are published, they are rigorously scrutinized by fellow scientists, ensuring that any conclusions drawn are not only supported by evidence, but are also free from biases and errors. This collaborative effort refines and strengthens the validity of scientific claims, helping to solidify the foundation of knowledge. Yet, even with these meticulous systems in place, flexibility remains a critical component of scientific work. The vastness of space is filled with unexpected phenomena that can alter the course of research. For instance, the discovery of a new celestial body or the identification of unforeseen conditions during a mission can challenge preconceived theories. The successful scientist is one who remains open to adjusting their hypotheses and methodologies in response to new data. Embracing this adaptive mindset is key to the ongoing process of learning and discovery in the ever-evolving field of space exploration. By combining structured methodologies, cutting-edge technological innovations, collaborative teamwork, and the ability to adapt to new evidence, scientists are able to manage the uncertainties that come with exploring the cosmos. These tools and approaches allow them to remain resilient in the face of the unknown and continue their relentless pursuit of knowledge. After all, the universe, with all its infinite possibilities, presents an ever-expanding frontier for human inquiry. One of the most profound and enduring areas of exploration in cosmology is the study of the universe's origin and evolution. Despite centuries of observation and research, many fundamental questions remain unresolved, tantalizing both scientists and enthusiasts alike. Perhaps the most perplexing of these mysteries is the nature of dark matter. While we have compelling indirect evidence of its existence, primarily from its gravitational effects on galaxies and other cosmic structures, its true composition remains elusive. What exactly is this invisible mass that appears to make up a substantial portion of the universe's total matter? Could it be composed of exotic particles that have yet to be discovered in our laboratories? This question lies at the heart of one of the most exciting fields of modern physics. Closely tied to dark matter is the enigma of dark energy, a force believed to be responsible for the accelerated expansion of the universe. While scientists can observe the effects of dark energy, its true nature remains a mystery. Is dark energy a constant, uniform energy density spread throughout space, or does its strength fluctuate over time? This question holds the potential to radically alter our understanding of the cosmos. If we can finally unlock the secrets of dark energy, we could gain profound insights into the ultimate fate of the universe itself. In addition to these enigmatic forces, there is the enduring mystery of the Big Bang. What triggered this cataclysmic event which marked the birth of our universe? And what was the universe like in its earliest moments? The conditions that existed before and during the rapid expansion of the Big Bang are still not fully understood, prompting scientists to explore a variety of theories. Some suggest quantum fluctuations at the tiniest scales, while others turn to multidimensional models that stretch the limits of imagination. The quest to understand the Big Bang remains one of the most compelling and exciting challenges in cosmology. Equally important is the search for a unified theory that can reconcile two of the most successful theories in modern physics: general relativity, which governs the behavior of large-scale structures like galaxies and black holes, and quantum mechanics, which explains the behavior of the smallest particles in the universe. This pursuit, often referred to as the challenge of quantum gravity, seeks to bridge the gap between these two frameworks, particularly in extreme environments like black holes or during the Big Bang itself. Understanding how these two forces interact could unlock new insights into the fundamental nature of space, time, and matter. Finally, there is the question of the future of the universe. As the expansion of the cosmos continues at an ever-accelerating rate, will it go on indefinitely? Or could there come a time when this expansion slows and reverses, causing the universe to collapse back in on itself? These scenarios are not merely hypothetical. They are deeply consequential, potentially shaping the ultimate fate of all matter and energy in existence. Exploring these possibilities is not just an academic exercise, it is a matter of uncovering the fundamental truths that govern our universe. The mysteries of the cosmos fuel endless discussions among cosmologists, as each question brings with it the potential for groundbreaking discoveries. These questions do more than challenge our intellect. They offer the possibility of unveiling deeper truths about existence itself, truths that could reshape our very understanding of the universe. The history of our understanding of the universe is rich with milestones that have fundamentally reshaped how we see our place in the cosmos. In ancient times, civilizations viewed the night sky through the lens of mythology, attributing the movements of the stars and planets to the actions of gods and deities. It wasn't until the ancient Greeks began to ask questions about the nature of the universe that these myths started to give way to more scientific explanations. Philosophers like Pythagoras and Aristotle proposed that the Earth might not be the center of the universe, and that celestial bodies could be governed by natural laws rather than divine will. The true revolution in our understanding came with the work of Nicholas Copernicus, who introduced the heliocentric model of the solar system. In this groundbreaking theory, Copernicus suggested that the sun, not the Earth, was at the center of our solar system. This radical idea shook the foundations of human thought and forced us to reconsider our place in the universe. The implications were profound. If the Earth wasn't the center of everything, what did that mean for humanity's role in the grand scheme of the cosmos? Johannes Kepler built on Copernicus's ideas by developing laws that described the motion of planets in elliptical orbits. Kepler's laws brought a mathematical precision to the understanding of planetary motion, emphasizing that the universe operated according to predictable, natural laws. His work laid the groundwork for the later development of physics and astronomy, providing the framework for future generations of scientists. Galileo Galilei's use of the telescope further revolutionized our understanding of the heavens. His observations of Jupiter's moons and the phases of Venus provided concrete evidence that the heliocentric model was correct. These discoveries not only advanced our understanding of planetary motion, but also underscored the importance of empirical evidence in shaping scientific theory. Galileo's work marked the beginning of a new era in observational astronomy, where direct observation and experimentation became central to the scientific method. In this way, the study of the cosmos has evolved from philosophical musings to a rigorous, evidence-based pursuit, driven by the constant quest for deeper understanding and knowledge. As our tools and methods continue to advance, the mysteries of the universe remain ever within our reach, challenging us to look ever deeper into the vastness of space and time. Furthermore, Sir Isaac Newton's groundbreaking formulation of gravity revolutionized our understanding of the universe. His laws of motion and universal gravitation described how celestial bodies interacted with one another through gravitational forces, offering a clear and predictable explanation for the motions of planets. This was more than a scientific breakthrough. It presented a framework for comprehending the behavior of objects, both on Earth and in the vast reaches of space. Newton's vision suggested a universe governed by specific, immutable laws, an orderly, predictable cosmos that starkly contrasted with the chaotic and random views that had dominated earlier thinking. His work laid the foundations for a shift in human perspective. No longer were we bound to an Earth-centered, anthropocentric worldview. Instead, we began to see a universe that was not only vast, but governed by natural laws, a place of wonder, mystery, and exploration. Newton's theories ignited a profound transformation in human understanding, sparking questions that continue to fuel the drive for exploration and discovery. The shift in perspective opened the door to modern astronomy, prompting an unending quest to unravel the mysteries of the universe and our place within it. This period marked a significant intellectual leap, from myth and superstition to science and empirical inquiry. Before Newton, ancient civilizations had already demonstrated a deep fascination with the cosmos, viewing celestial events as both meaningful and divine. Events such as solar eclipses, meteor showers, and the movements of planets were seen not merely as astronomical phenomena, but as signs, omens, and divine messages. These events were intricately woven into the mythologies, rituals, and agricultural practices of these societies. For them, the sky was far from a passive backdrop. It was a living entity that communicated the will of the gods, offering guidance for daily life. Take the ancient Egyptians, for example. They regarded the sun as a powerful deity, and celestial events were often interpreted as foretelling earthly happenings. Their towering pyramids, meticulously aligned with stellar phenomena, stand as a testament to their advanced understanding of astronomy. The Shabaka stone, an ancient Egyptian artifact, preserves a creation myth that intertwines the origins of the cosmos with the birth of the world itself, symbolizing the profound connection between the heavens and earth. Similarly, the Maya civilization exhibited a deep celestial knowledge. They constructed sophisticated observatories and devised highly accurate calendars that enabled them to predict solar and lunar eclipses with astonishing precision. Their culture was so entwined with astronomy that their artifacts, carved stelae, pottery, and murals, depict celestial interpretations and integrate the heavens into their religious practices. The Maya saw the cosmos as a reflection of divine order, an intricate dance of time and space that dictated the rhythm of their lives. In Mesopotamia, the Babylonians also kept detailed records of astronomical observations etched onto clay tablets. These observations were not for mere curiosity. They were intimately linked with agriculture, guiding the timing of planting and harvesting, as well as predicting seasonal weather patterns. Babylonian artifacts, such as star charts and depictions of planetary movements, reveal their deep respect for the cosmos and their desire to decode its patterns, reflecting an early, sophisticated approach to observational astronomy. These ancient societies crafted tools, like sundials and early astrolabes, to observe and measure the heavens, demonstrating a profound desire to understand the universe and the forces at work within it. Even today, monuments such as Stonehenge stand as lasting symbols of humanity's connection to the cosmos. These structures not only served as calendars, but also as places of ritual and spiritual significance. Through the remnants of these civilizations, we gain a glimpse into how their inhabitants navigated life by the stars, shaping their cultures and worldviews around the movements of celestial bodies. The field of cosmology has been dramatically reshaped by several key breakthroughs in observational science. Each of these milestones has provided new insights that challenged and refined existing theories about the universe. One of the most pivotal moments in the history of astronomy occurred with the invention of the telescope in the early 17th century. This revolutionary tool enabled astronomers like Galileo Galilei to peer more deeply into the night sky. Galileo's observations, such as the moons orbiting Jupiter and the phases of Venus, provided compelling evidence for the heliocentric model of the solar system, challenging the long-standing geocentric view that placed Earth at the center of the universe. As we moved into the 20th century, new discoveries further transformed our understanding of the cosmos. One of the most groundbreaking revelations came with the detection of cosmic microwave background radiation. This faint, pervasive glow, which fills the universe, is the remnant heat from the Big Bang, providing irrefutable evidence for the theory that the universe began in a massive explosion. This discovery offered a crucial framework for understanding the early moments of the universe and its subsequent expansion. Another transformative development came in the 1920s with Edwin Hubble's observations of distant galaxies. Hubble found that these galaxies were moving away from us, an observation that led to the realization that the universe is expanding. This discovery was instrumental in solidifying the Big Bang theory and in shaping our current understanding of the universe's origins. In the late 20th century, astronomers made even more significant strides. Precise measurements of supernovae and the discovery of dark energy revolutionized our understanding of the universe's fate. It was revealed that not only was the universe still expanding, but that its expansion was accelerating, an unsettling yet fascinating finding. This acceleration is driven by an unknown force, dubbed dark energy, and it has profound implications for our understanding of the universe's future. Will the universe continue expanding forever, or will it eventually contract? Will it reach a state of equilibrium, or will its expansion hasten towards a dramatic conclusion? These questions continue to fuel scientific inquiry as we seek to understand the ultimate fate of the cosmos. Through each of these milestones, humanity's understanding of the universe has deepened, challenging old assumptions and sparking new questions. The journey is far from over, And with each discovery, we are drawn deeper into the mysteries of the universe, continuing a quest that began millennia ago with the first gazes of ancient civilizations towards the night sky. Advancements in technology, particularly through the development of space-based observatories like the Hubble Space Telescope, have revolutionized our understanding of the universe. These incredible tools have allowed us to peer deeper into space than ever before, bypassing the atmospheric limitations that once constrained our observations. As a result, we've made remarkable discoveries, one of the most profound being the identification of exoplanets. This revelation has transformed our understanding of planetary systems and sparked new questions about the potential for extraterrestrial life beyond our own solar system. But these breakthroughs have done more than just expand our knowledge. They have forced us to rethink the very framework upon which our scientific understanding is built. With each new discovery, the cosmos has grown both clearer and more complex. The more we learn, the more we realize how much remains to be explored. These advancements invite scientists to continuously challenge existing theories, pushing the boundaries of what we thought we knew. The universe, once a mysterious and unfathomable expanse, now seems a little less enigmatic, but in its place lies an even deeper complexity. At the heart of this ever-expanding inquiry are the fields of quantum physics and cosmology, which, despite seeming to operate in completely separate realms, are intertwined in profound and surprising ways. Quantum physics is the study of the tiniest building blocks of matter, particles whose behavior often defies our everyday intuitions. In stark contrast, cosmology explores the grand scale of the universe, studying phenomena like the birth, evolution, and large-scale structure of galaxies and stars. However, one of the most critical intersections between these two fields emerges in the study of the early universe, particularly moments after the Big Bang. In those first moments, the universe was an incredibly hot and dense environment where quantum effects were not just important, they were essential. The very fabric of space-time itself was shaped by quantum mechanics during this era. To understand the events of the earliest universe, models that integrate both quantum mechanics and cosmological dynamics are crucial. Without this combination of perspectives explaining the rapid expansion of the universe and the behavior of particles in its earliest stages would be nearly impossible. As we dig deeper into the mysteries of the cosmos, the concept of black holes brings these fields together once more. Black holes are one of the most fascinating and enigmatic phenomena in space, and their event horizon, the boundary beyond which nothing can escape, poses a significant challenge to our understanding of reality. According to the principles of quantum physics, any information that falls into a black hole should not be lost. Yet this notion directly contradicts classical physics, which has long held that anything crossing the event horizon is essentially erased from the universe. This paradox has sparked years of debate and led to theories that attempt to reconcile quantum mechanics with the gravitational forces at play in black holes. Additionally, the concept of quantum fluctuations offers a new way of thinking about the formation of cosmic structures. In the early moments of cosmic inflation, a period of rapid expansion following the Big Bang, tiny quantum fluctuations were stretched across vast distances. These fluctuations, while minuscule, played a crucial role in shaping the universe as we know it, eventually giving rise to galaxies and large-scale structures. This connection between quantum processes and the observable cosmos is a perfect example of how the smallest, most fundamental forces can have monumental consequences on the grand scale. The blending of quantum physics and cosmology challenges not just our understanding of the universe, but the very nature of existence itself. Whether we are probing the earliest moments of the universe, unraveling the strange complexities of black holes, or investigating the birth of galaxies, we continue to uncover the intricate, often surprising relationship between the microscopic and the monumental. As we do, our perception of reality itself is undergoing a profound transformation. Quantum phenomena have raised several intriguing challenges to our classical understanding of the cosmos. At the center of these phenomena is the concept of quantum entanglement, where particles become so deeply connected that the state of one can instantaneously affect the state of another, regardless of the distance separating them. This defies our intuitive understanding of locality, suggesting that information could potentially travel faster than the speed of light, a notion that goes against one of the cornerstones of Einstein's theory of relativity. Another mind-bending concept is superposition, which states that particles exist in all possible states at once, only settling into a specific state when they are observed. This idea forces us to reconsider the nature of reality itself. Could it be that the universe exists in multiple configurations simultaneously, only choosing one when it interacts with an observer? This concept has profound implications, not just for how we understand quantum particles, but for how we perceive time and space on a grand scale. Black holes, too, present a quantum enigma that stretches our understanding. According to classical physics, once an object crosses a black hole's event horizon, it is lost forever. But quantum mechanics introduces a radically different idea: Hawking radiation. This theory suggests that black holes might emit radiation and lose mass over time, gradually evaporating and challenging the conventional view of black holes as eternal, inescapable traps. These quantum effects also influence the behavior of matter on a larger scale, such as in the cosmic microwave background radiation, the faint glow left over from the Big Bang. This radiation offers clues to the quantum processes that shaped the early universe, revealing the impact of quantum mechanics on the cosmos at large. The intersection of quantum mechanics and general relativity in cosmology remains one of the most profound and unresolved issues in modern physics. The complex interplay between these two domains, one governing the very small, the other governing the very large, has led to a series of puzzles that continue to challenge scientists. As we probe deeper into the universe, the very principles that form the foundation of our understanding of the cosmos are being questioned and reevaluated. Quantum theories open a fascinating window into understanding anomalies in deep space, those phenomena that traditional physics struggles to explain. One such anomaly is the disparity between the visible matter we observe in the universe and the gravitational effects it produces. This discrepancy has led scientists to postulate the existence of dark matter, an invisible substance that seems to exert a gravitational pull on visible matter. Quantum theories suggest that particles we cannot yet detect might be interacting with regular matter in ways that we don't fully understand, creating gravitational effects we can't yet explain. Moreover, quantum entanglement, this mysterious connection between distant particles, raises the possibility that events separated by vast distances might be interconnected in ways we cannot yet comprehend. This idea hints at a deeper, more intricate fabric of reality than we currently realize, one that could help explain mysterious energy signatures or fluctuations detected in cosmic backgrounds. Quantum fluctuations, the idea that energy levels fluctuate at microscopic scales, could also influence the behavior of galaxies and cosmic radiation. This opens up new avenues for explaining unexpected outcomes in the observed behavior of galaxies or the distribution of dark matter. Such anomalies, rather than being dismissed as oddities, might be crucial clues that reveal new aspects of the universe's structure and origins. By providing a new lens through which to view these mysteries, quantum theories give scientists a toolkit for investigating some of the deepest questions about the cosmos. Perhaps, by examining the very small, we can finally begin to unravel the cosmic puzzles that have baffled astronomers for centuries. As our understanding of the universe deepens, simulations have become indispensable tools in visualizing and comprehending the vast and complex structures of the cosmos. Given the immensity of the universe and the complexity of the physical laws that govern it, observing these phenomena in real life would be impossible. Through simulations, scientists can create three-dimensional representations of cosmic events, such as the formation of galaxies or the behavior of dark matter, revealing patterns that might otherwise remain hidden. These simulations act as virtual laboratories where the laws of physics are applied to recreate and study the behavior of the universe. By adjusting parameters like the amount of matter or energy involved, scientists can simulate a wide range of cosmic scenarios and test different theories. This allows researchers to explore outcomes and refine their hypotheses without waiting billions of years for events to unfold naturally. These simulations are, in many ways, the future of cosmological research, offering a powerful tool to probe the deepest questions about the universe's origins and evolution. Simulations play a pivotal role in visualizing the early universe, offering an invaluable tool for scientists to recreate the conditions just moments after the Big Bang. By doing so, they allow us to explore how the universe expanded and evolved, providing crucial insights into its formation. These virtual experiments serve as a window into the cosmos, allowing researchers to test ideas and hypotheses while helping to answer fundamental questions about the structure of the universe. For example, they help us understand why galaxies cluster together and the intricate role gravity plays in shaping the fabric of the cosmos. Moreover, simulations serve a dual purpose. They not only provide a platform for testing scientific ideas, but also transform abstract theoretical concepts into tangible, visual representations. This visualization brings the complex workings of the universe into clearer focus, making it easier for both scientists and enthusiasts to engage deeply with the material. By offering detailed visual representations of cosmic events, simulations foster a more profound understanding of the universe we inhabit. They bridge the gap between theory and reality, helping both the scientific community and the general public appreciate the vast scale of cosmic phenomena. One of the most significant contributions of simulations lies in their role as virtual laboratories for testing theories in cosmology. These simulations allow scientists to recreate the vast and often complex events of the universe within a controlled setting, free from the constraints of time and space that limit real-world observations. By inputting initial conditions based on our current understanding of the laws of physics, researchers can simulate how cosmic structures evolve over billions of years. They might simulate everything from the gravitational interactions between galaxies to the formation of stars, or even the movement of elusive dark matter. Through these simulations, scientists can visualize phenomena that are often beyond the reach of direct observation. For example, while we cannot directly observe the merging of galaxy clusters or the behavior of matter around black holes in real time, simulations provide a way to study these processes in detail. The true power of simulations lies not just in their ability to replicate existing phenomena, but also in their capacity to generate predictions. When a simulation predicts the distribution of galaxies in a specific region of space, and that prediction aligns closely with data from telescopes, it strengthens the underlying theoretical models. Conversely, if significant discrepancies are found, these simulations often lead to a re-evaluation of existing theories or a deeper exploration into the physical laws that govern the cosmos. As computational technology continues to advance, the sophistication of these simulations increases. New methods allow researchers to incorporate increasingly complex factors, such as cosmic inflation or the influence of dark energy, into their models. This iterative process, running simulations, refining theoretical models, and comparing results with empirical data, serves as an essential feedback loop in deepening our understanding of the universe. Ultimately, simulations are an indispensable tool in cosmological research, transforming abstract theories into vivid, dynamic models that can be observed, analyzed, and tested. Researchers frequently use computer simulations to explore phenomena that are beyond our direct observational capabilities. These simulations act as virtual laboratories where complex cosmic processes, such as the formation of galaxies, the behavior of black holes, or the explosion of supernovae, can be recreated in exquisite detail. To create these simulations, scientists begin by establishing physical models grounded in our current understanding of fundamental forces, gravity, electromagnetism, thermodynamics, and translating them into mathematical equations that describe how cosmic systems evolve over time. Once these models are in place, researchers use powerful supercomputers to solve the equations, simulating billions of particles that represent stars, gas, and dark matter. These particles interact according to the known laws of physics, providing a highly detailed simulation of cosmic evolution. Over time, as the simulation progresses, scientists can witness the formation and movement of galaxies or observe the merger of massive black holes. These events, which in reality take millions or even billions of years, can be compressed into moments, allowing researchers to examine processes that would otherwise be beyond reach. In addition to simulating cosmic phenomena, researchers also compare their findings with actual astronomical data. For example, they may look for patterns or behaviors in observational data, like the light emitted by distant stars or the gravitational waves produced by cosmic events, that match the results of their simulations. By validating their simulations against real-world observations, scientists can refine their models, improving their accuracy and making better predictions about the future. This approach helps bridge the gap between known physics and the mysterious realms of the universe that remain largely unexplored. Simulations allow us to examine cosmic events that are otherwise too distant, too faint, or too complex to study directly. In doing so, they enable us to understand the forces that shape our universe, from the smallest particles to the largest structures. The study of meteorites, asteroids, and comets further expands our understanding of the cosmic ecosystem, each playing a unique and essential role in shaping the solar system and influencing life on Earth. Asteroids, which are rocky remnants from the early solar system, are primarily found in the asteroid belt located between Mars and Jupiter. These celestial objects act as time capsules, preserving materials from the solar system's formation. Scientists study asteroids to uncover the building blocks that contributed to the creation of planets, offering a window into the early solar system's chemical and physical conditions. Some asteroids even contain valuable resources, metals and minerals, that may one day become important assets for humanity through space mining. Beyond the rocky remnants, comets add another dimension to our understanding of the cosmos. These icy bodies, often originating from the distant reaches of the solar system, such as the Kuiper Belt and the Oort cloud, are like dirty snowballs floating through space. As they approach the sun, their ice vaporizes, creating beautiful sweeping tails that stretch for millions of kilometers. Comets have long been regarded as harbingers of change, but their significance may go far beyond folklore. They may have played a critical role in delivering water and organic compounds to Earth billions of years ago, contributing to the conditions that allowed life to take root. As these icy visitors pass through the solar system, they provide invaluable clues about the early chemical makeup of the solar system and the potential for habitability on distant worlds. Meteorites, which are fragments of asteroids or comets that survived their fiery fall through Earth's atmosphere, offer direct samples of these celestial objects. By studying meteorites, scientists can gain insights into the materials that formed Earth and other planets. Some meteorites contain amino acids, the building blocks of life, suggesting that the ingredients for life might be more widespread throughout the universe than previously thought. These findings continue to shape our understanding of the origins of life on Earth and the potential for life beyond our planet. Together, meteorites, asteroids, and comets form an integral part of the cosmic narrative, helping scientists decipher the history of our solar system and offering tantalizing hints about the possibility of life beyond Earth. Their interactions with planetary atmospheres and environments can have far-reaching consequences, as impacts from these objects can both create and destroy, shaping the development of planets and their ability to support life. In this cosmic drama, these celestial bodies play essential roles, preserving the history of the solar system and influencing its future. Moreover, observations of moons, particularly those orbiting the gas giants, unveil a captivating range of geological and atmospheric processes that reveal the dynamic nature of our solar system's evolution. For instance, moons like Europa, one of Jupiter's many satellites, are believed to harbor subsurface oceans beneath their icy crusts. This fascinating discovery raises the possibility that these oceans could support life, posing intriguing questions about the potential for life beyond Earth. Such findings prompt scientists to explore the broader question of life's distribution throughout the universe. The study of these distant moons, often through advanced telescopes and exploratory spacecraft missions, has shed new light on the theories of planetary formation and migration. By analyzing the orbits of these moons, scientists are able to understand the complex gravitational interactions that have shaped the positions of celestial bodies across eons. This gravitational dance has led to the current configuration of our solar system, revealing much about its formation process. Thus, these moons and other celestial objects serve not only as building blocks of our solar system, but also as key pieces of evidence in unraveling its intricate history. The data we gather from these objects helps to trace the evolutionary steps that led to the system we observe today, offering a glimpse into the cosmic past that stretches back billions of years. In addition to moons, the study of space rocks, such as asteroids and meteoroids, holds vital clues about potential threats to Earth and the origins of our solar system. These objects, which can vary in size and composition, often pass close to Earth's orbit, posing a potential risk. Scientists carefully monitor their movements and physical characteristics, gathering essential information that could inform us of what might happen should one of these celestial bodies collide with our planet. Understanding the orbits of these space rocks is a critical aspect of this research. By tracking their movements, scientists can predict the paths these objects might follow in the future. This knowledge is crucial for identifying which asteroids and meteoroids could pose a danger to Earth. Given the gravitational influence of other planets and moons, even small changes in an asteroid's trajectory can have significant long-term effects on its path. Over millions of years, these small shifts can drastically alter an asteroid's orbit, potentially leading to a collision with Earth. But it's not just their orbits that interest scientists, it's also their composition. Some asteroids are considered remnants from the early solar system, preserving a snapshot of the conditions that existed at the time of the planet's formation. By studying the chemical makeup of these space rocks, scientists gain a deeper understanding of the types of materials that were present in the early solar system and how they could affect Earth if they were to collide with our planet. The size and structure of these asteroids also determine the impact they might have. Larger, denser asteroids could cause more significant damage, while smaller ones might create less catastrophic effects. In addition, studying the scars left by past impacts on Earth, such as craters, gives scientists insight into the potential consequences of future collisions. Evidence from both our planet and the moon serves as a record of how different meteoroids, varying in size and speed, have had a wide range of environmental impacts, from localized destruction to global catastrophes. This history provides valuable data on how future impacts might play out, helping us prepare for the possibility of another devastating collision. The study of these space rocks also fuels ongoing efforts to devise protective strategies for Earth. By mapping the locations and movements of asteroids, scientists aim to develop early warning systems to alert us of potential threats. Furthermore, researchers are exploring ways to deflect or divert an asteroid on a collision course with Earth, whether through direct impact or gravitational manipulation. These defensive measures, though still in early stages, are crucial for enhancing our preparedness against cosmic threats and ensuring the continued safety of our planet. Beyond physical observations, scientists study the evolution of celestial bodies over vast cosmic timescales using a combination of techniques. Observational tools, including powerful telescopes, allow astronomers to peer deeply into the universe, capturing light across a broad spectrum of wavelengths: visible, infrared, and radio waves. This diverse range of observations provides a wealth of information about the age, composition, and dynamic behavior of stars, planets, and galaxies. By observing how these objects behave, scientists can piece together the intricate processes that drive their formation and evolution. The study of light emitted or absorbed by celestial bodies plays a central role in this research. By analyzing the spectrum of light from distant stars and galaxies, astronomers can determine an object's temperature, chemical composition, and velocity. For instance, by identifying specific patterns in the light, researchers can deduce whether a star is moving toward or away from Earth. This information is invaluable for understanding gravitational interactions, the structure of galaxies, and the movement of celestial bodies within the universe. Beyond direct observations, theoretical models provide a framework for predicting how celestial bodies evolve. These models incorporate the fundamental laws of physics, including gravity, nuclear fusion, and thermodynamics. They simulate complex processes like star formation, the birth of planetary systems, and even the eventual fate of galaxies. By adjusting variables within these models, scientists can explore a wide range of scenarios, offering insights into the life cycles of stars, the formation of new planets, and the eventual end of galaxies. Computer simulations take this a step further, enabling astronomers to model interactions in space with incredible accuracy. These simulations can illustrate how celestial bodies collide, how they change composition over time, or how entire galaxies evolve and interact over billions of years. By comparing these simulations with real-world observations, researchers can fine-tune their models, offering ever more precise predictions about the future evolution of the cosmos. Through these multifaceted approaches, ranging from detailed observations to advanced simulations, scientists continue to uncover the mysteries of our universe. Their work helps us understand not only the history of our solar system and its celestial bodies, but also the broader processes that govern the evolution of galaxies and the universe itself. This ongoing research brings us closer to understanding the grand cosmic narrative, a story that stretches back billions of years and will continue to unfold for billions more. Studying ancient celestial objects like population 2 stars, which are among the oldest known to humanity, offers a profound window into the early days of our universe. These stars, often referred to as the cosmic fossils, harbor secrets of the first elements that formed after the Big Bang. By studying the light they emit, scientists can decipher the chemical makeup of the universe as it existed billions of years ago, revealing how it has transformed since. This investigation involves a sophisticated blend of observation, theoretical analysis, and computer simulations, allowing researchers to piece together the puzzle of cosmic evolution. It's a multidimensional approach that not only illuminates the birth and death of celestial bodies, but also unravels the underlying forces that shape the very structure of the universe. Looking forward, the future of the universe presents a fascinating and dramatic transformation. Over an unimaginably long span of time, galaxies will reshape themselves in a chaotic cosmic ballet. Collisions and mergers will become common, dramatically altering the shape of the night sky. Our own galaxy, the Milky Way, is on a collision course with the Andromeda Galaxy, an event set to unfold in about 4 billion years. When these two cosmic giants collide, it will trigger a cataclysmic burst of star formation and gravitational interactions, forever reshaping both galaxies. However, this event is only the first step in a larger cosmic evolution. As galaxies continue to collide, the dynamics of the universe will become increasingly complex and chaotic. At the same time, the fates of individual stars will also play a crucial role in this transformation. Some stars will burn out in spectacular explosions, such as supernovae, while others will collapse under their own gravity, forming neutron stars or black holes. These stellar remnants will add yet another layer to the fabric of the universe, creating dense regions of gravity that warp space-time itself. These regions will have a profound impact on the surrounding cosmos, bending the very nature of space and time. As the universe continues to expand, driven by the enigmatic force known as dark energy, galaxies will gradually drift farther apart. Over time, the local group of galaxies, which includes the Milky Way, may become one of the few remaining visible clusters in a vast, dark expanse of space. Eventually, the majority of galaxies will recede beyond the reach of our telescopes, causing our once vibrant night sky to fade into an ocean of darkness. Looking even further into the future, around 100 trillion years from now, the universe will enter a state known as the cosmic dark age. By then, most stars will have burned out, and galaxies will be scattered across an ever-expanding void. The universe will be left in an eerie quiet, with only the remnants of stars, white dwarfs, neutron stars, and black holes, drifting in the cold emptiness. As the universe continues its inexorable march toward entropy, all that will remain is a quiet, lonely cosmos. This state will eventually culminate in what is known as heat death, where the universe reaches a uniform temperature and all processes cease. The vibrant and dynamic cosmos we see today will have transformed into a still, lifeless expanse, an eternal silence where nothing changes. The future of the universe, though distant and unimaginable, tells a story of profound change, evolution, decay, and a slow, inevitable transition into tranquil darkness. These future events unfold on timescales so vast that they challenge our understanding of time itself. On Earth, we live by the rhythm of days, seasons, and years, marked by the rising and setting of the sun. This steady cadence offers a comforting familiarity, grounding our daily lives. However, when we shift our perspective to the scale of the cosmos, time stretches in ways that are almost beyond comprehension. In the universe, events unfold over millions, even billions of years. The life cycle of a star, from its formation in the swirling gases of a nebula to its explosive death as a supernova, takes place over timescales that dwarf the entire span of human existence. Even the death of a star, which might occur after billions of years, is but a brief moment in the vast history of the universe. In human terms, this is an eternity, but in the cosmic scale, it is only a blink of an eye. The universe's story is one of relentless change, from the birth of the first stars to the slow decay of everything into a quiet, cold void. As we ponder the fate of the cosmos, we are reminded of the fleeting nature of everything around us and the immense timescales that shape the ever-evolving universe. Moreover, the influence of gravity adds a further layer of complexity to our understanding of time, especially in the vicinity of massive objects like black holes. Time itself behaves very differently in these regions. It slows down relative to areas further away. For an observer close to a black hole, time would seem to pass more slowly than for someone situated far from its immense gravitational pull. This phenomenon vividly illustrates that time is not a uniform experience across the universe. As we venture further into space, particularly with the help of advanced telescopes and spacecraft that explore distant galaxies and cosmic phenomena, we begin to realize the sheer vastness of time itself. These discoveries compel us to rethink not only how we measure time, but also how we perceive our place in the universe. What may feel like a significant, defining moment on Earth can appear as nothing more than a fleeting flicker when viewed in the context of the immense expanse of the cosmos. This awareness forces us to see our existence as part of a much larger and ongoing story, one that unfolds over inconceivable stretches of time. As humanity continues its ambitious quest to explore the universe's final frontier, we are increasingly relying on advanced tools and methods to enhance our observational capabilities. At the forefront of this exploration are ground-based telescopes, which have undergone a remarkable transformation through cutting-edge technology. These instruments utilize adaptive optics, a technique that adjusts the shape of telescope mirrors in real time to counteract the blurring effects caused by Earth's atmosphere. This revolutionary approach allows astronomers to capture images that rival those obtained by telescopes in space. Complementing this, space-based observatories have marked a significant leap forward in our exploration efforts. By positioning themselves above the atmosphere, these telescopes avoid the distortion caused by air and can capture clearer, more detailed data across a wider range of light wavelengths, including infrared and ultraviolet. A prime example of this leap is the James Webb Space Telescope, which is capable of peering deeper into space than any of its predecessors. Webb's advanced instruments have unlocked critical insights into the formation of stars and galaxies that emerged in the early days of the universe, shortly after the Big Bang. But the wonders of space are not confined to optical observations alone. Radio telescopes, which detect radio waves emitted by celestial bodies such as pulsars and distant galaxies, open up new avenues for exploration, allowing scientists to study cosmic phenomena invisible to optical telescopes. The Square-Kilometer Array, set to be the most extensive radio telescope ever built, promises to revolutionize our understanding of the origins of cosmic structures and the evolution of the universe itself. In addition, gravitational wave detectors, like the Laser Interferometer Gravitational Wave Observatory, LIGO, have added another layer to our observational toolkit. These instruments are capable of detecting ripples in space-time caused by cataclysmic events such as black hole mergers that would otherwise remain undetected by conventional telescopes. Gravitational waves offer us a completely new way of observing the cosmos and understanding events that emit little or no visible light, thereby expanding our reach far beyond traditional methods of detection. As the volume of astronomical data increases exponentially, artificial intelligence and machine learning are stepping in to assist astronomers in making sense of it all. These technologies allow scientists to identify patterns, classify objects, and even predict upcoming cosmic events, helping us uncover insights from vast datasets that would have been too complex or unwieldy to analyze manually. The convergence of these innovative tools and methodologies is rapidly bringing us closer to uncovering the many mysteries that lie beyond our current observational capabilities. With each new breakthrough, we inch ever closer to a fuller understanding of the universe. One of the most significant advantages of space observatories is their ability to provide a clear, uninterrupted view of the universe, free from the distortions caused by Earth's atmosphere. When we observe the night sky from our planet, light pollution and air turbulence can obscure our view, making it difficult to capture the full richness of the cosmos. However, space observatories, situated far above this atmospheric veil, allow us to see celestial objects in their true form. These observations reveal intricate details and phenomena that would otherwise be hidden from view, offering astronomers an unprecedented level of clarity. By observing across various wavelengths, such as infrared, ultraviolet, and even X-rays, space-based telescopes can uncover a wealth of information about the universe that would otherwise remain out of reach. For instance, infrared observations can expose cooler objects such as distant planets or interstellar dust clouds, while X-ray observations reveal high-energy processes taking place around black holes or in the aftermath of supernova explosions. This multi-wavelength approach allows researchers to build a more comprehensive picture of cosmic events and structures, further enhancing our understanding of the universe. Space observatories also offer the advantage of continuous monitoring, unimpeded by the day-night cycle or unpredictable weather conditions on Earth. This constant observation allows for the collection of long-term data, which is invaluable for studying dynamic phenomena, such as the life cycles of stars or the evolution of galaxies over vast stretches of time. Insights gained from these long-term studies can lead to groundbreaking discoveries about fundamental questions, including the nature of dark matter, the formation of the universe, or the potential for life on other planets. Collaboration between space observatories and research institutions around the globe plays a key role in accelerating our discoveries. By sharing data and findings, scientists can work together on ambitious projects that push the boundaries of our knowledge. This global effort enriches our understanding of the cosmos and speeds up the pace of discovery. As technology continues to advance and new observatories are deployed, our ability to explore remote regions of the universe will only expand, further deepening our connection to the cosmos and revealing more of its profound mysteries. Interestingly, amateur astronomers also contribute significantly to the field of cosmic exploration. Although they typically lack the high-tech equipment used by professional astronomers, these dedicated enthusiasts often make important discoveries from their own backyards or local parks. Amateur astronomers are particularly valuable in the discovery of transient events, such as supernovae, asteroids, and comets that might otherwise go unnoticed. Through their persistent monitoring of the night sky, these individuals can identify changes or anomalies that are crucial for understanding the cosmos. Many of these events occur swiftly, sometimes lasting only a brief moment, making the vigilance of amateur astronomers essential for capturing these fleeting cosmic phenomena. In sum, the combination of advanced technology, innovative tools, and global collaboration has propelled our exploration of the universe to new heights. As our capabilities continue to evolve, so too will our understanding of the vast and mysterious cosmos in which we reside. Each discovery brings us one step closer to unraveling the secrets of the universe, and each breakthrough offers us a deeper connection to the awe-inspiring forces that govern the cosmos. Amateur astronomers often collaborate with professional teams, becoming active participants in citizen science projects. These initiatives are designed to invite non-experts to contribute to scientific endeavors, often through data collection, analysis, or both. Through such collaborations, amateurs significantly enhance the overall output of scientific research. Their shared passion for astronomy drives them to go beyond mere observations, engaging deeply with online communities to exchange findings, discuss techniques, and offer insights. This collective sharing of knowledge can, in turn, lead to new discoveries as they contribute fresh perspectives to ongoing research. In addition to making valuable observations, many amateur astronomers have played a crucial role in improving the quality and accessibility of astronomical data. Utilizing advanced imaging techniques and software, tools that were once reserved exclusively for professionals, they have elevated the precision of their work. This expanded access to cutting-edge technology allows them to refine their observations and integrate them into larger scientific conversations. In some remarkable instances, the work of amateurs has even resulted in new theories or revisions to existing knowledge about celestial phenomena. While amateurs might not have the same vast resources as professional astronomers, their enthusiasm, keen observations, and collaborative spirit make them invaluable partners in the quest to unlock the mysteries of the cosmos. Their efforts have enriched our collective understanding of the universe, making astronomical research not only more inclusive, but also more dynamic. As our knowledge of the cosmos expands, so too does our understanding of humanity's place within it. Every new discovery, whether it's about distant galaxies, intricate stellar formations, or even the basic building blocks of life on far-off celestial bodies, invites us to reflect on our own existence. For example, the discovery of extremophiles, organisms that thrive in Earth's most hostile environments, suggests that life is far more adaptable than we ever imagined. This realization opens the door to the possibility of life on other planets or moons, where conditions were once thought too harsh to support living organisms. As we explore exoplanets, planets that exist outside our solar system, it becomes apparent that there may be billions of worlds capable of harboring life. This challenges the long-held belief that Earth is unique in its ability to support life and raises profound questions about the vastness of the universe. Are we truly alone? Or is humanity just one small piece of a much larger cosmic puzzle? Moreover, our exploration of cosmic events such as black hole formation and the behavior of dark matter deepens our understanding of the universe's fundamental structure. These discoveries also provide valuable insights into the universe's history and future, as well as prompting deeper philosophical inquiries about the origins of existence itself. As we delve into these complex cosmic processes, it becomes evident that we are part of a magnificent living universe with its own story, one that we are only beginning to understand. Advanced telescopes and space missions continue to uncover new dimensions of the cosmos, challenging previous assumptions about our place in the grand scheme of things. Our home planet, once thought to be the center of the universe, is revealed to be a tiny speck in the vast, ever-expanding cosmos. This shift in perspective inspires both humility and curiosity, propelling humanity to explore, learn, and ultimately strive to understand not just our place, but also our purpose within this vast, mysterious universe. Understanding the universe doesn't just expand our knowledge, it also shapes our future aspirations. The more we learn about the cosmos, the more we are motivated to explore and expand beyond the confines of our home planet. As we uncover the secrets of celestial bodies, cosmic phenomena, and the fundamental forces that govern the universe, this newfound knowledge lays the foundation for future exploration. A deeper understanding of our own solar system, its planets, moons, and asteroids, directly informs the path forward for human exploration and settlement. Mars, for instance, is a prime candidate for future missions, offering valuable clues about the availability of water in the past, and the potential for life. Such missions could also pave the way for human settlement, opening new frontiers for resource utilization and the long-term sustainability of our species. The study of asteroids, many of which are rich in metals or even water, presents opportunities for further exploration. Mining these celestial bodies could provide essential materials, offering a sustainable way to supply Earth and future space missions with the resources they need. This vision of resource utilization is no longer a distant dream, but a practical goal made more achievable by our growing knowledge of the universe. In parallel, advancements in space technology such as propulsion systems, life support technologies, and habitat construction are directly informed by our study of distant worlds. As we gather more data about the conditions on exoplanets and other celestial bodies, we can begin to design spacecraft that are more efficient, cutting travel times significantly. The knowledge we gain also allows us to create habitats that can support human life far from Earth. Understanding the effects of long-term space travel, such as cosmic radiation and the impact of microgravity on the human body, helps us develop solutions to protect astronauts on extended missions. These advancements are crucial to ensuring the safety and well-being of those who venture into the great unknown. Finally, as we learn more about exoplanets, what they are composed of, how they form, and whether they might be capable of sustaining life, we fuel our imagination and further our exploration ambitions. The possibility that life could exist elsewhere deepens our understanding of biology, evolution, and the conditions necessary for life to thrive. This, in turn, paves the way for future interstellar exploration, where humanity may eventually reach beyond our solar system, seeking to answer the age-old question: are we truly alone in the universe? The answers to these questions hold the potential to reshape our understanding of life itself, offering new possibilities for discovery and exploration in the vast expanse of space. As humanity's awareness of the universe continues to evolve, a profound sense of global unity takes root, one that transcends borders and encourages the pursuit of a common goal, the exploration of space. This collective drive fosters cooperation among nations, businesses, and individuals, each contributing their knowledge, resources, and vision to a shared endeavor. The spirit of collaboration not only enables us to pool our resources, but also instills the potential for peace and unity among the diverse peoples of Earth. As we expand our understanding of the cosmos, we become increasingly capable of exploring it, embarking on incredible journeys beyond our home planet. Empowered by knowledge, humanity stands on the threshold of unprecedented exploration, with the potential to discover new worlds and unlock the vast resources of the universe. The more we understand about the universe, the better equipped we become to navigate its many mysteries. The idea of colonizing distant planets, once relegated to the realm of science fiction, now occupies the forefront of scientific and philosophical discussions. However, this vision of expansion brings with it a host of ethical questions that demand our attention, questions that will shape the future of our species in profound ways. At the heart of these concerns is the concept of stewardship. As we look to the stars, we must ask ourselves, are we ready to become caretakers of celestial bodies, ensuring that we do not disrupt the delicate balance of ecosystems, even in the most remote corners of space? Every planet, moon, and asteroid carries with it a unique history, a set of conditions that may harbor the potential for life, however small or microscopic. It is our responsibility to protect these pristine environments from contamination and exploitation, to preserve them not only for future generations, but for the unknown life forms that may exist within them. Furthermore, if we encounter extraterrestrial life, we are confronted with another set of moral dilemmas. What rights do these potential life forms have? Whether in the form of microorganisms or more complex beings, any discovery of alien life will demand careful reflection on our ethical obligations. The temptation to exploit these life forms for human benefit must be weighed against the imperative to respect their right to exist undisturbed, free from interference. Humanity's history of colonization on Earth provides a sobering backdrop for these ethical discussions. The legacy of colonization, fraught with violence, displacement, and the erasure of indigenous cultures, serves as a reminder of the dangers of unchecked expansion. As we consider the colonization of other worlds, we must approach it with extreme caution, respect, and humility. It is crucial that we engage in open dialogue about the benefits and risks of off-world colonization, asking who will benefit and who may be harmed in the process. The question of autonomy for future space settlers arises as well. Should they have the right to govern themselves? And how can we ensure that space settlements are equitable and inclusive? The ethical considerations extend beyond just the potential for colonization. The extraction of resources from other planets introduces dilemmas that mirror those we face on Earth. How can we responsibly harness the wealth of space without repeating the mistakes of our past, where resource exploitation led to environmental degradation, inequality, and social injustice? The prospect of mining asteroids or extracting materials from other worlds must be approached with the same careful consideration given to sustainable development here on Earth. The long-term impacts on the interplanetary environment as well as the distribution of wealth and resources must be factored into any plans for resource extraction. The philosophical implications of humanity's journey into the cosmos are equally profound. What does it mean for our species to reach for the stars? What does this ambition say about our identity, our purpose, and our place in the universe? These questions transcend the realm of science and technology, tapping into deep questions of existence and meaning. As we venture beyond the confines of our home planet, we must ensure that our journey is guided by a framework that emphasizes responsibility, respect, and thoughtful reflection. In doing so, we can ensure that our cosmic aspirations align not only with our survival, but also with our ethical duty to the broader universe. As we continue to explore the cosmos, the importance of collaboration across various scientific disciplines becomes increasingly clear. The universe, in all its complexity, is a vast, interconnected system. Phenomena in one area of space can influence and provide insights into other regions, creating a dynamic web of relationships that we are only beginning to understand. For instance, astronomers rely heavily on physics and mathematics to decode the behavior of distant stars and galaxies. Without these fundamental tools, much of the data we gather from telescopes would remain largely unexplained. The marriage of theoretical principles with empirical observation has led to groundbreaking discoveries that reveal the intricate workings of the universe. In addition to astronomy, the study of celestial bodies frequently intersects with such as geology and biology. Planetary scientists, for example, examine the surface and atmospheric conditions of distant planets, drawing upon the knowledge of Earth's geological processes to make educated predictions about the makeup of other worlds. This collaboration allows scientists to identify conditions that might support life elsewhere, comparing the environments of distant planets with those found on Earth. Understanding how life thrives on our planet offers valuable insights into what might be required for life to exist beyond Earth. Engineering also plays a crucial role in space exploration. The construction of spacecraft and the development of advanced telescopes require specialized knowledge and technology, without which we would be unable to embark on missions to far-flung destinations. The partnership between engineers and scientists is vital to the success of these endeavors. Engineers design and build the tools that make exploration possible, ensuring that spacecraft can withstand the harsh conditions of space, while scientists use them to collect vital data. Together, they make possible extraordinary achievements, such as sending probes to distant planets and capturing the first-ever images of black holes. These accomplishments not only enhance our understanding of the cosmos, but also unlock mysteries that would otherwise remain hidden. As we continue to venture into space, the synergy between disciplines, astronomy, physics, biology, engineering, and more, holds the key to unlocking the universe's most profound secrets. This collaboration is not just about advancing technology or expanding our knowledge. It's about working together as a global community to ensure that our exploration of the stars is guided by principles that reflect our highest ideals. Only then can we begin to understand our place in the vast, interconnected universe and perhaps find a way to protect and preserve it for generations to come. Computational science has emerged as a vital force in unraveling the mysteries of the universe by analyzing the vast data sets generated by modern observations. With the aid of sophisticated algorithms and simulations, scientists from an array of disciplines ranging from physics to astronomy to computer science work in unison to uncover insights that would be impossible for any one field to reveal alone. This collaborative effort provides a more complete and nuanced understanding of cosmic events, bringing together multiple perspectives to create a clearer picture of the universe's complexities. A striking example of this approach can be found in the study of gravitational waves, where experts from diverse scientific domains join forces to decode the signals emitted by violent cosmic events. Through this interdisciplinary cooperation, we build a richer tapestry of knowledge. By blending diverse techniques, methodologies, and perspectives, we are better equipped to address some of the most profound and enduring questions about the cosmos. The outcomes of these collective efforts are not only groundbreaking discoveries, but also a deeper appreciation of our place within the universe. This endeavor reveals not only the nature of the distant realms beyond our planet, but also highlights how deeply interconnected and dynamic the universe truly is. The more we understand, the more we realize that the universe is far from static. It is a vast and ever-evolving system in which every part influences the others. International organizations play a crucial role in facilitating this wide-reaching collaboration. By providing the platforms for cooperation, these entities help unite scientists, researchers, and policymakers from around the globe to tackle the immense challenges that affect us all. These global bodies focus on issues that transcend borders, such as climate change, public health, and space exploration, that demand unified efforts. Through their support, these organizations enable the sharing of resources and expertise across nations, ensuring that every corner of the world contributes to the broader pool of knowledge. One of the most important functions of international organizations is the provision of financial support for large-scale research initiatives. By investing in these endeavors, they ensure that scientists have access to the funding necessary to push the boundaries of discovery. This support fosters cross-border collaboration, allowing teams from different countries to work together on common objectives and removing barriers that often hinder scientific progress. Additionally, these organizations create guidelines and establish standards to maintain the quality and integrity of research. With shared criteria for evaluating results, it becomes much easier to compare findings from different parts of the world and ensure that conclusions drawn are reliable and universally applicable. Furthermore, international organizations are instrumental in promoting capacity building and the transfer of knowledge between developed and developing regions. By providing training and educational resources, they ensure that the global research community remains diverse and inclusive. This inclusivity enriches the collective understanding of complex issues, enabling a wide range of perspectives and innovations to emerge. In this way, these organizations not only advance scientific research, but also ensure that the benefits of knowledge are spread equitably across the globe. Through the fostering of cooperation and the dissemination of knowledge, they contribute to technological advancements that improve lives and help solve the challenges facing humanity. As we turn our gaze toward the vastness of the universe, we confront a landscape full of mysteries that have captivated the human imagination for centuries. From the formation of stars to the elusive nature of dark matter, the universe poses questions that require a wide array of perspectives to answer. To make progress in answering these questions, scientists from multiple disciplines must join forces, each contributing their unique methodologies, knowledge, and expertise. For example, astronomers focus their efforts on observing celestial objects, searching for clues to the universe's workings. Meanwhile, physicists apply theoretical models to interpret the forces at play within those very objects. When these two fields collaborate, they form a more holistic understanding of the cosmos. But this collaboration extends beyond just astronomy and physics. The contributions of engineers and computer scientists are indispensable as well. Engineers design the advanced telescopes that allow astronomers to peer deeper into the universe, capturing clear images of faraway galaxies. At the same time, computer scientists create complex algorithms to process and analyze the vast amounts of data gathered from these missions. Each discipline brings its own tools and techniques to the table, combining technical expertise with creative problem solving. This cross-pollination of ideas is essential for breaking new ground in our quest to understand the universe. Beyond the realm of pure science, the inclusion of diverse cultural perspectives can also offer valuable insights. Indigenous knowledge systems, for example, offer alternative views on the night sky, which can challenge conventional scientific paradigms and inspire new avenues for exploration. These diverse cultural perspectives contribute to a more holistic view of the universe, reminding us that our understanding of the cosmos is not a monolithic, one-size-fits-all interpretation, but a tapestry of ideas shaped by many voices. In scientific teams, backgrounds from different cultures and disciplines encourage open dialogue and collaboration. By testing assumptions and questioning long-held beliefs, these diverse teams foster innovative thinking that would be difficult to achieve in homogeneous groups. This synergy between different scientific, technical, and cultural backgrounds fuels breakthroughs that no single discipline could achieve alone. It is through this collective intelligence that we inch closer to decoding the fundamental workings of the universe and our place within it. However, observing distant galaxies and cosmic phenomena is no simple task. The challenges faced by astronomers are immense, stretching the limits of our technology and our understanding of the cosmos. One of the most formidable obstacles is the vastness of space itself. Light from distant celestial objects takes millions or even billions of years to reach us, meaning that we see these objects as they were in the past, not as they are in the present. This time delay complicates our ability to accurately interpret the current state of these objects, making it difficult to draw precise conclusions about their behavior. On top of this, the universe is filled with obstacles that obscure our view. Dust and gas clouds can block the light from distant galaxies, making it hard to capture clear images. It's like trying to see a lighthouse on the horizon through a dense fog, where crucial details are hidden from view. To counteract this, astronomers use a variety of techniques, including the use of infrared telescopes. These specialized instruments can penetrate through the dust clouds, allowing scientists to gather important data that would otherwise be obscured. Another challenge arises from the expanding universe. As galaxies move away from us, their light is stretched to longer wavelengths, a phenomenon known as redshift. This shift means that light emitted by distant galaxies may fall into the infrared or radio spectrum rather than the visible light we are most familiar with. To study these distant galaxies, astronomers must use instruments that are capable of detecting emissions in these non-visible wavelengths. The sheer number of faint objects scattered across the sky also makes observations difficult. The background noise created by stars, cosmic radiation, and other celestial phenomena can overwhelm the signals from distant galaxies. It's like trying to hear a whisper in a crowded room. Important details are often drowned out by the constant static. However, advancements in imaging technology and the development of more powerful telescopes have allowed astronomers to filter out this noise, helping them focus on the signals that matter most. In sum, the challenges of observing and understanding the cosmos are immense, but through technological innovation and collaboration across disciplines, scientists are steadily making progress in their quest to unravel the universe's deepest secrets. Space exploration and the study of the cosmos have always been driven by a desire to uncover the mysteries of the universe. Yet, despite the advances in technology that have enabled us to peer deeper into the fabric of space, there remain significant limitations that challenge our understanding and progress. The advent of powerful telescopes and spacecraft has revolutionized our ability to observe distant galaxies and cosmic phenomena, providing clarity that was once unimaginable. However, these advancements come at a high price, not only in terms of the financial costs, but also the engineering complexities involved in designing and launching these instruments. Every new breakthrough in space exploration pushes the limits of what we can observe, but it also introduces new challenges, requiring increasingly sophisticated technologies and meticulous planning. At the core of this challenge lies the extreme environment of space, which presents numerous obstacles. Space is a place of high radiation levels, intense temperature fluctuations, and a vacuum that poses a threat to delicate equipment. The distance between Earth and distant galaxies, for example, requires us to confront not just physical obstacles, but the very fundamental problem of scale. The vast emptiness between celestial objects creates a unique set of challenges in communication and observation. Moreover, the universe itself is expanding, which introduces additional complexities, as scientists must contend with the cosmic effects of this expansion on their observations. Space technology has become a game of adaptation and innovation. The sheer harshness of space means that space must be equipped with shielding capable of absorbing harmful radiation and insulating sensitive equipment from extreme heat changes. For instance, some spacecraft are covered with specially designed materials that protect against solar radiation and prevent equipment from freezing in the cold depths of space. But technology does not stop at building resilient machines. It extends to ensuring that these machines can continue to function under extraordinary conditions. Communication, for example, is one of the most critical hurdles. Spacecraft located millions or even billions of kilometers away take a considerable amount of time to receive and send signals. This delay complicates real-time data transmission. To address this, space researchers have developed autonomous systems that can operate independently, make decisions on site, and conduct experiments without waiting for instructions from Earth. These autonomous systems can process data right where they are, reducing the need to send large amounts of data back and forth across vast distances. Power supply is another area of concern. Solar panels, which are the most common energy source for spacecraft, become less effective the farther they get from the sun. To solve this, scientists are investigating alternative power sources, such as nuclear reactors, that can provide a reliable and consistent energy supply for deep space missions. This technology ensures that spacecraft can continue functioning even in regions of space where sunlight is scarce or non-existent. As space missions grow more ambitious, ensuring the reliability of technology becomes a priority. The complexity of these missions means that even a single failure could jeopardize an entire exploration. To mitigate this risk, engineers build multiple layers of redundancy into spacecraft systems. These backup systems are designed to take over should any primary component fail, providing an extra layer of security that ensures mission success. This redundancy also enables a more diverse and resilient approach to the challenges posed by deep space. For deep space exploration to thrive, it requires a multidisciplinary approach. Engineers, scientists, and researchers must collaborate across fields, combining their knowledge to create solutions that will allow humanity to push deeper into the cosmos. It is this spirit of innovation that makes space exploration not only a pursuit of scientific discovery, but also a testament to human ingenuity. Each new technology, whether it's an improved propulsion system, more efficient life support systems, or the integration of robotics and artificial intelligence, enables us to explore further and deeper into space. One of the critical areas for future exploration is propulsion technology. Current propulsion systems often limit the speed of spacecraft, making missions to distant stars or planets a daunting task that could take decades or even centuries. Technologies like nuclear thermal propulsion or ion drives, which are far more energy efficient than conventional methods, could drastically shorten the time it takes to travel to far-off destinations. Such developments would make interstellar missions far more feasible, opening up possibilities for exploration that were once the stuff of science fiction. As missions progress and the prospect of sending humans deeper into space becomes a reality, the need for reliable life support systems grows ever more urgent. Long-duration space missions, such as those planned for Mars or beyond, will require habitats that can recycle air, water, and food, reducing the need for constant resupply from Earth. The development of systems that can grow food in space or convert waste materials into usable resources is vital to sustaining life during extended voyages. In addition to these advancements, the role of robotics and artificial intelligence (AI) cannot be overstated. Advanced robots equipped with AI could perform tasks that are too dangerous or difficult for humans, such as repairing spacecraft or exploring planets where human presence is not feasible. These robots could explore the surface of Mars, analyze soil samples, and even study the icy moons of Jupiter or Saturn. The capabilities of AI in space exploration go beyond simple automation. These systems will be able to think critically, make decisions, and adapt to the unpredictable nature of space environments. Another frontier in space exploration is communication. Current systems rely on radio waves to transmit data between spacecraft and Earth, but these signals can be slow and vulnerable to interference. New research is investigating the potential of laser communications, which promise to deliver faster, more reliable, and more secure data transmission. Laser-based systems could enable near-instantaneous data transfer, making it possible to send real-time updates from distant space missions, transforming our understanding of distant worlds. Technological advancements in observation tools are also progressing rapidly. New telescopes capable of observing different wavelengths of light, from infrared to ultraviolet, are allowing scientists to detect and study celestial phenomena that were previously hidden from view. These telescopes will enable the identification of exoplanets and the analysis of their atmospheres, providing critical insights into the potential for life beyond Earth. Each breakthrough in telescope technology brings us closer to understanding the universe's origins, structure, and even the possibilities of life elsewhere. Yet, while technology continues to push forward, so too does the vast mystery of the universe itself. Despite our technological capabilities, many of the cosmos's most intriguing elements remain elusive. Dark matter, which constitutes about 26% of the universe's mass energy content, remains undetectable through traditional means. It does not emit light, but its presence is inferred from its gravitational effects on galaxies. Similarly, the phenomenon of cosmic inflation, the rapid expansion of the universe just moments after the Big Bang, helps explain the uniformity observed in the cosmic microwave background radiation, a remnant of the Big Bang that still fills the universe today. Other cosmic phenomena, like the vast number of galaxies estimated at over 2 trillion, reveal the immense scale of the universe. Yet, despite these numerous galaxies, most of the universe is a cold, empty expanse. The distances between galaxies are so vast that they often exist hundreds of thousands of light years apart, creating a sense of cosmic loneliness. And even within galaxies, the material is spread out in a way that highlights the sheer emptiness of the cosmos. But it's not just emptiness that defines the universe. It's full of strange and remarkable phenomena like rogue planets, worlds that do not orbit a star but drift aimlessly through space. There could be as many rogue planets as stars in the Milky Way, each potentially hosting its own unique conditions for life. The universe also operates on principles that lead to extreme phenomena, such as neutron stars, the incredibly dense remnants of collapsed stars. A sugar cube-sized amount of neutron star material would weigh as much as several mountains on Earth. Additionally, the concept of multiverses, the idea that our universe could be just one of many, each with different physical laws, offers a tantalizing glimpse into an even broader and more complex reality. Whether or not multiverses exist is still a topic of speculation, but it challenges the way we view our existence and the nature of the universe itself. The universe is a complex, intricate, and ever-expanding tapestry. Every detail, whether large or small, contributes to the larger narrative of our cosmic story. From the smallest particles to the most distant galaxies, each element plays a crucial role in shaping our understanding of the cosmos. The interactions between these elements, be they particles, dust, or light, reveal patterns that inform theories about everything from the formation of stars to the eventual fate of the universe. The study of these small details has led to groundbreaking discoveries, such as the detection of dark energy, which is believed to be responsible for the accelerated expansion of the universe. New findings suggest that dark energy may not be a constant force, but rather something that changes over time. Similarly, research into exoplanets has revealed that planets far different from Earth could also harbor life, expanding our understanding of what makes a planet habitable. In the field of galaxy evolution, scientists have been surprised to find that galaxies previously thought to be in decline are in fact still actively forging new stars. This discovery challenges our understanding of how galaxies evolve over time and suggests that the universe may not be as predictable as once thought. With the detection of gravitational waves, ripples in space-time caused by events like black hole mergers, researchers are now able to directly observe cosmic events that were once only theoretical. These waves have provided new insights into the behavior of black holes and other extreme cosmic phenomena, reshaping our understanding of the universe's most mysterious entities. Each of these discoveries, while seemingly minor on its own, is a piece of the puzzle. Together, they show that the universe is far more complex and dynamic than we ever imagined. As technology advances and our understanding deepens, we are on the verge of unlocking even more mysteries, propelling us forward into the next chapter of human discovery. The cosmos, vast and full of surprises, remains an endless source of curiosity and wonder.